Awesome. Um, Thanks everyone for being here. I really wish I could be there in Colorado right now, but I'm happy to present my work online. So my name is Renato Bragheri. I'm a research scientist at Caltech and NASA JPL. And today I'm going to talk about tray-based vegetation optical properties and how that can impact future projections of climate. I would like to thank my collaborators that are span across Caltech and JPL, but also the UK. So I think this slide is just an overview, and probably for this crowd is you already know what I'm gonna say. But Earth system modeling is useful to model physical processes to help us to understand and predict how the Earth system interacts and responds to natural changes, human activities, but also internal variability and so on. And so in these two first plots I show here at the top, it's from a paper that we published a couple of years ago showing the net biome production in the above domain. So the NASA above domain is the Arctic boreal region where NASA conducted a decade of intense field campaigns and airborne campaigns. And we wanted to see what the Earth system models from CMIP 5 and 6 were predicting as to until the end of the century. And we see that, we know that across scenarios and across models, we have a lot of variability. And it's optimistic to see that the spread across models in the future is reducing from one version of CMIP to the next, not necessarily for the right reasons, but we see that the spread of models is decreasing and they are converging. In another study that we published a few years ago as well, we evaluated the difference in soil albedo between the broadband, so just two broadbands, the PAR and the near infrared bands, versus the hyperspectral representation of soil albedo at 5 nanometers resolution. And when we calculate the propagated radiative force into the climate system, we see that by simply changing the model from broadband to hyperspectral, we get a radiative forcing of 3.55 watts per meter square, which is quite substantial. And so the IPCC report lists, for some of the reasons these models have a lot of uncertainty, is that transfer of radiation, water, and heat in the vegetation soil atmosphere continuum are treated very simply in these global ecosystem models. And so another way to look at this question of simplicity in these models is to think biodiversity, right? So usually in Earth system models, we represent biodiversity via plant functional types. And so plant functional types are this representation of broad groupings of plant species that share similar characteristics in ecosystem function. And why do we use PFT until nowadays? Well, PFT has made sense in the beginning of the land modeling effort because we lived in a very data poor world. And so we lacked observations of all the variables needed to represent a grid cell, within grid cell heterogeneity. But not only that, PFTs are useful because they simplify our lives, really. So we can get a list of lookup tables of variables that we're not very sure or we have very few observations. And we assume that these variables will, plants of similar characteristics, like the tropical forest, for example, in this figure here, they share similar characteristics. And so we classify them as the same PFTs. Well, they are time invariant. Most of these variables are time invariant. And so there's a problem there in representing these variables across space and time. But it's a useful simplification for the things that we're looking at global scale. The question is, are PFTs a sufficient representation of biodiversity in our system models? And what I'm going to look at in this presentation is how trait diversity might add another layer of representation of the heterogeneity in our system models. So I'm focusing on this first part on the radiative transfer scheme. And so I'm not going to go through the all variables linked to PFTs, but rather a few variables related to the spectral properties of vegetation. And so we use the two-stream scheme because it's a very efficient model. So it requires very few parameters and it's computationally efficient, but it divides the short wave radiation spectrum in two broad bands. So the photosynthetically active radiation that goes from 400 to 700 nanometers, and the near infrared from 700 to 2500 nanometers. And so in a world where our satellites were observing very broad bands, it made sense to make a land surface model that agree with those broad bands. But now that we live in this era where more and more hyperspectral sensors are starting to orbit the planet, does it make sense to make our Earth system models a little more complicated and a little more spectrally resolved um, to account for some of the uncertainties in the radiative balance of the planet? Well, it's also important to say that when we go hyperspectral, we can start to get signatures from the plants that are related to traits, plant traits. So for example, here in the image, we see that the visible is highly linked to chlorophyll content, but then we see that the end of the spectrum is related to cell structure, lignin, proteins. So now if we start going hyperspectral, we can start to have a more holistic view of plants, going away from the plant functional type approach and using a more trait-based approach. So in this exercise that I'm going to show here, I asked the question if that matters. And to do so, I'm going to ask, what is the canopy spectral property between PFT and a trait-based approach? And then what is the impact of that on climate and carbon simulations? So a little bit of the methodology that we use here. So we developed a global map of canopy spectral properties using a leaf chlorophyll content map derived from MV Maris. And so if you remember that first global figure I show where the Amazon basin is a whole single plant functional type, and we look here at the chlorophyll map in figure A, we see that within the Amazon basin, we have a lot of variance in chlorophyll content. And so that map of chlorophyll was then used in the ClimaLand model. Well, the ClimaLand model is the model that we've been developing at Caltech and MIT for the past 5 years or so. It's a model that is written in Julia and has a hyperspectral radiative transfer scheme. And it also has a way to calculate optical properties from biophysical parameters. And so we use the ClimaLand model to calculate the optical properties, leaf reflectance and transmittance in both broadbands used in CLM to calculate then these variables from leaf traits. And what we did was then replace that PFT lookup table that is shown here by the spatially represented map of optical traits, of optical properties of the canopy, and we ran the couple CSM2. I want you to pay attention, for example, if you look at the third column there, that is the alpha leaf visible, and you can see that these variables are the same across many PFTs. And so these values were obtained from, old field measurements over a very limited number of sites. And so it's really something that has a lag effect. We haven't paid attention much to that, but I will show here that it could be particularly important. And so when we calculate now the differences in surface albedo in the far and near infrared regions between the PFT and traits, we can get differences of up to 10% with this dipole behavior where the tropics show a negative bias and the extratropics show a positive bias in both bands. And when we look then at the couple results, the couple model results, we see that differences in radiative fluxes can exceed 5 watts per meter square and can change the skin temperature of up to 0.4 degrees, which could be quite substantial. We observe these differences across the climate system, including energy, water, carbon variables. And when we perform an independent evaluation with MODIS surface albedo, we see a better agreement in tropical par and near infrared albedo in comparison to MODIS from the trait case in comparison to the PFT case. When we look at carbon, we see that because of this duality, the boreal regions responding one way and tropical regions responding another way, we see higher GPP in the extratropics due to improved light penetration and low vapor pressure deficit. And in the tropics, we see reduced GPP due to increase in stress conditions, just hotter. And when we perform future simulations with these trait maps, we see that although the total number is less than 1 petagram of carbon per year, it can increase the discrepancy between the trait and PFT can increase in the future. And so this was the story related to the optical properties of the radiative transfer code. But I just want to finish with another example of where traits can be impactful on the climate system. So if we think about the main differences between CMIP 5 and 6 models across the board, we can name probably the inclusion of nutrient dynamics as the main thing that is common across every single CMIP 6 model now has some sort of nitrogen representation. And so the way we think nitrogen impact climate is by impacting, for example, VC max or CN ratios, or the carbon cost of acquisition of nutrients, or changes in soil biogeochemistry. And so all these things impact climate indirectly via the carbon sink. So this nitrogen impacts the carbon sink, which will impact the climate indirectly. But now I would argue that nutrient dynamics might also have a direct impact on climate, where the CN ratio can change the leaf optical properties, and that could change surface albedo and impact the climate directly. So this is just another example of how trait variability could impact the climate. And so just to conclude, in this talk, I show that the biases between the PFT and trait cases can be really impactful for climate and the carbon sink. And that we argue that new generation Earth system models should think about including more trait bias parametric, trait-based parametric variability in order to account for some of these uncertainties in climate and carbon projections, making it a little more complicated, but a little more accounting for the internal variability of within PFTs, but also the temporal variability of some of those values. Thank you very much.
Should we give enough time? Do we have enough time for a question or two? And I don't know if there were any online. Anyone? Abby?
Yeah, but can I talk to them?
Are the microphones on? Okay.
Great, thank you. That's really interesting. And I have a couple things I like to follow up on to learn more about, but just a logistical question. Did you kept plant functional types, you just updated their optical properties based on your better estimates from using traits of plants, is that right?
Correct.
Do you think that's good enough? Like, because essentially, you know, a reconceptualization of plant functional types is that you just reimagine them to be the relevant combinations of traits that you need. Like, you have to discretize in some way. So is updating these properties like a good first step rather than kind of restructuring the entire model, which is going to be harder to do if you're not starting from the beginning?
Yeah, that's a great question. And I think your answer is within your question, right? Like to change the model from a PFT approach to a totally trait-based approach will be a nightmare, right? We have so many variables that are not tractable to traits, but are dependent on PFTs, and that are not observable from space, like things related to root distribution or hydraulic properties of plants that are very hard to capture from space. But I argue that the things that we can capture from space and that are linked to a PFT currently, for example, the optical properties of the canopy, those things we should start to, because those will be easy fixes, and they can be quite impactful. So, yeah.
All right, so we'll move on to the next speaker.
Thank you.
Thank you, Renato. Next speaker is Lily Zhang. Also remote.
Is that working? Everyone
Yes,
hear
we can
me?
see your screen. So you may begin.
Great. Hi, everyone. This is Lily Zhang. I'm a third-year graduate student at the University of Washington working with David Battisti, and today I'm really excited to share some of my recent work setting up the soil moisture depletion experiments within CLM to study teleconnection-like behaviors in Western US climate. The motivation for our work comes from a previous study where we were analyzing summertime temperature variability over the Western United States. And what we found in that study is that year-to-year variations in summertime temperature across this region are captured by the leading pattern I'm showing here on the right. We call this pattern the Western US summertime temperature pattern. And the positive phase of this Western US summertime temperature pattern is associated with warmer than average temperatures during the months of June, July, August across the domain, but particularly over the Northwest where it's really red there on the graph. The pattern's warm phase is also accompanied by negative precipitation and soil moisture anomalies during the summertime months over the Northwest. So essentially what we're finding is that from year to year, temperatures during summer tend to vary in this very spatially coherent way. And when it's hot, it tends to also be dry, which might not be too surprising to you all. But what was surprising about our summertime temperature pattern is that it's not well correlated with ENSO or any other traditional metrics of SST variability, which we might typically think of as being like the dominant modes in climate variability. Instead, we find that summertime temperatures have this really intriguing relationship to antecedent variations in hydrologic conditions. So what I mean by that is, if we take the summertime temperature pattern, which I have there on the right, and we regress it against various seasonal moisture anomalies in our observations, we find that this negative correlation between summertime temperature and moisture that we see during the months of June, July, and August go as far back as the preceding spring and winter season. So there's this negative correlation between summertime temperature and moisture in the Southwest during spring and winter. What's might be like a really nice result in today's session where we're hearing a lot about how models don't capture things well is that actually the CSM captures this relationship between antecedent hydrologic conditions and summertime climate quite well. It's not only the CSM, there's a few other GCMs which aren't pictured. They all capture this relationship between moisture deficits in the Southwest during spring and winter, and then subsequent warming and drying in the Northwest US during summer. So this leads to the question, how can we explain this relationship between distal moisture anomalies and summertime climate that we're finding in both our models and in our observations? And if we take a first stab at that, we just disregard what I think is a fairly straightforward connection between wintertime precipitation and its influence on spring soil moisture. The real mystery is the second part of the pathway and this question of what allows springtime soil moisture deficits all the way down there in the Southwest to influence summertime temperature and moisture in the Northwest. So in other words, what is this teleconnection-like behavior we're observing between these two distal regions that's occurring on seasonal timescales? In order to answer that question and also determine whether what we're seeing is actually causality, whether spring soil moisture deficits are able to produce this summertime temperature response, I designed these soil moisture depletion experiments in CSM2. So here on the left, I'm showing an example of what soil moisture might typically look like at the start of spring in a CLM restart file. And in my experiment, what I do is I take that restart file and I deplete all the soil liquid water content in the top 3 model layers. So I set it to 0 in the restart file on March 1st. And the model setup that I'm using for my control run is CAM6, so coupled land atmosphere, pre-industrial forcings, and importantly, prescribed climatological SSTs. In order to sample across a variety of starting conditions for both the land surface and the atmosphere, I create this 110 member ensemble by first running our control run for 110 years. And then within that control run, I pinpoint every March 1st, and I branch off to duplicate the restart file and deplete soil moisture, as I was just showing, over the Southwest. So once I have that, I can run my depleted restart file for a year to create this alternate timeline that I can then subtract against the control run to get anomalies as a result of our experiment. And all the results that I'm going to be showing from here on out are representing anomalies averaged across our entire 110 member ensemble. And so I want to emphasize that because we created this ensemble, our results are not dependent on initial conditions in the, besides the soil moisture depletion in the land or the atmosphere, also not dependent on internal variability. And recall that the SSTs are prescribed to climatology, so these results also don't depend on SST coupling or any sort of variability in that system. I'm going to start off by showing the near surface temperature response to our March soil moisture depletion. So here on the left, I'm just showing the result of our soil moisture depletion on the average 10 centimeters soil moisture for the month of March. And we see that encouragingly, even though we were only doing this one-time change to the restart file, it did manage to affect the average for March in like a noticeable way. And when we look at the near surface temperature response, we find 2 interesting things that I'm going to highlight in today's talk. So the first is that there's this cooling in March that's happening over our area of depletion in the Southwest US. Might be sort of not what we were expecting. And then what we were expecting is that there's this warming in late spring, early summer across the Northwest US that is very reminiscent of our observed temperature pattern. So first, I'm just going to talk a little bit about the cooling in March that we see. I think it's something really neat and unexpected is going on there, where we have this decrease in the average near surface temperature that's consistent with a decrease in net downwelling shortwave radiation at the surface. But there's not really much of a change in cloud fraction. And here I'm just showing low cloud fraction. There's not much of a change in cloud fraction at all. And instead, we think what's explaining this cooling and this decrease in surface shortwave is increased surface albedo just as a result of drying. So some of you might be familiar with this aspect of the model, but also reality where wet soil appears darker than dry soil. And we think that's what's just by depleting all the soil moisture in March, we were able to affect the albedo enough to create this cooling response that we see. Now, moving on to May, June. In May and June, we see that there's a warming response in the Northwest and generally across the Western United States that's consistent with our observed pattern. So again, in observations, we found that when there's warming in this red area, that's typically associated with soil moisture deficits where it's brown down here in the Southwest. So this is great. And as for what's causing the temperature response, well, there's an increase in the net downwelling surface shortwave that's very consistent with a decrease in low cloud fraction. And so, you know, this is just the warming is a direct consequence of the shortwave cloud radiative effect, where there's less low clouds the albedo decreases and we have greater surface shortwave. And these low cloud changes are consistent with more larger scale patterns in precipitation. So large scale precipitation and humidity also decrease in the same areas where our low cloud fraction is decreasing. So we think that ultimately the warming is driven by these large scale circulation changes that I'm showing here. So this is the 700 millibar geopotential height for the months of March, April, and May. You see that starting in March, there's this circumglobal pattern that sets up. And again, everything I'm showing here is anomalies averaged over our ensemble number. What we're finding is that there's this pretty consistent circulation response that we think is ultimately what's causing these changes in large scale moisture that then affect temperature through the shortwave cloud radiative effect. Okay, so about these circulation changes, the fact that our local depletion is able to affect circulation on such a large scale might seem like a bit of a stretch, but it's actually very consistent with what previous studies have found. So there are a number of previous studies that have shown that local diabatic heating anomalies can generate these quasi-stationary wave response patterns that look a lot like what we're seeing. And I want to highlight two studies in particular, Koster et al. 2016 and Tang et al. 2019, that demonstrate within a GCM just drying the soil, the surface moisture in the small regions enough to produce this pattern. Here on the right, I'm just showing an animation of the changes in 400 millibar geopotential height starting from day one of our experiment, and it's looping back over now. But what we see is that like around week 2, there's this like large scale pattern that sets up that's what we're observing in the monthly mean. Okay, the only problem, as you might recall, is that there was actually cooling on average over the Southwest in March. So that would sort of contradict our hypothesis about how diabatic heating over our dry surface can excite these stationary wave anomalies. When we dug into the temperature changes a little bit more, we found that there's this, even though the minimum daily temperature decreases considerably, the maximum daily temperature does actually increase. So as a result of drying the soil, there's this like wider diurnal temperature range where we have greater heating during the daytime, and then at night there's more cooling, and overall there's less energy in the system, so that's why we see the cooling response in the average. And so our hypothesis was that maybe this daytime heating is enough to extend into the upper troposphere and sort of ping on the jet to excite this stationary wave response. And so to confirm that hypothesis, I reran my experiments with only 50 ensemble members at 3-hourly resolution. And when we look at the vertical temperature profiles for March, so this is height and pressure coordinates, and this is time. So this is temperature, and this is the vertical heat flux. We see that during the daytime, there are these like spikes of heating, these temperature warming that extends all the way into the upper troposphere and is very consistent with our theory for how daytime heating over the dry surface could extend all the way up there and excite this wave response. So I'm gonna stop here and summarize and just say that what we're showing is in both models in CSM2 and in observations, springtime soil moisture deficit can drive summertime warming in distal regions. And we find that this response, because of the way we set up our experiments, is independent of both atmospheric and SST variability. So it's solely due to land-atmosphere coupling. The way that these soil moisture anomalies are able to affect climate is first they have this local effect on the surface albedo that causes surprising cooling in March, but then extending forward to summer, they have this circumglobal effect on the circulation patterns that is reminiscent of like a stationary wave response to diabatic heating. The implications of our study, one, it has massive implications, I think, for predictability on seasonal timescale. So if we're able to establish this link between preceding hydrologic conditions and then an expectation for what summertime climate would look like, that would be a new source of predictability in the region. And lastly, I think it's really cool to, look at and think about how soil moisture can produce these large-scale teleconnection-like behaviors. So with that, I want to thank everyone for your time. This is my first time attending the land model working group meeting, but I'm excited to be involved in the future as well, and love to hear your questions.
All right. Are there any questions online? None yet. Okay, so let's. Meg, you want to ask your question?
Yeah, Lily, this is awesome work. Thank you for sharing it. I have so many questions, but I'm wondering, so you zeroed out soil moisture over the Southwest.
Yeah.
Do you have a sense of how much of an anomaly in soil moisture you need in order to get a warming signal in June, July, and August? Like, what if it's not zeroed out? What if it's, 50% drier or 60% drier? Like, how much drier than normal does it have to be in order to get a temperature response?
Yeah, that's a great question. So one thing I will note is I think the response in the models is a little bit weaker than in observations, which is why I kind of hit it with a sledgehammer and depleted all the moisture. In observations, the correlation between the temperature anomalies in summer, which are around 0.8 degrees Kelvin, and the springtime soil moisture anomalies is pretty high, and it's much weaker in the models. So in observations, even just a 10% change in soil moisture is has some correlation with the summertime temperature response. But we found that was much weaker in the models. Your talk earlier made me think a lot about these questions. So one thing, for example, is because I'm only doing this one-time depletion, the effect of that on the March average soil moisture is not that great. But in the Tang et al. Study, where they did a similar experiment in summer and they depleted moisture and found the circumglobal circulation change, they tried it with a bunch of different depths of moisture and also different magnitudes of moisture, and they found that the pattern doesn't change, but the magnitude of the temperature response changes. So I think we would expect to see what we're really trying to point out is this spatially coherent blob pattern that's centered on the Northwest. It's very similar to what the Tang et al. Study found, and it's consistent between our observations and models, but I think the magnitude would probably just depend a little bit on the moisture anomaly. Yeah.
Thanks, Lily.
All right, thank you. Shall we move on to the next? All right, next speaker, Hanjun Kim. Can you share your screen and unmute yourself, please?
Okay.
And the title will be The Underestimated Runoff Decline to Warming Climate Models. And I'm putting the emphasis on the right.
Okay.
We can hear you. We can't see your screen yet.
Oh, yeah. Thank you. Oh, so. Can you see my screen?
Yes.
Okay, thank you. So, hello everyone. My name is Hanjun Kim, and I'm postdoc working with Flavio Lenner at Cornell University. This work is also advised by Dr. Andy Wood, Dr. Dave Lawrence, and other anchor scientists. So today, I want to talk about the underestimated runoff declines in Earth system models. First of all, why do we use ESM to look at the runoff, even if there are hydrological models? Only ESM simulate the interactions between climate systems, which is essential for projecting climate change. So for the future world resource assessment, runoff projections from ESMs are now being utilized. For example, the recent study estimates the global urban population facing water scarcity directly using Series 6 runoff output. So it is 0.93 billion people in present day, but it will become 1.7 to the 2.4 billion people in the future. And the large uncertainty range here mostly comes from the Series 6 runoff output. So we need to reduce this uncertainty. Then what is the source of this uncertainty? The primary source would be the uncertainty in meteorological forcing. First, precipitation responses are main driver of runoff and they are highly uncertain. Temperature responses are incomplete proxy for evapotranspiration, but the temperature response itself is relatively robust compared to precipitation. However, runoff projections are generally more uncertain than either precipitation or the temperature projections. This indicates the additional uncertainties at the land surface. In other words, each model have different sensitivity of runoff to the same amount of precipitation or the temperature responses. We think the uncertainty in this runoff sensitivity would be related to the fact that the runoff generation processes regarding the warming are complex. For example, since warming occurs with the CO2 increases, there are complex vegetation feedback. Stormwater closure can lead to enhancement of runoff, but at the same time, vegetation greening can lead to the decrease in the runoff. And the snow or glacier melt with the warming can directly increase the runoff. However, the resulting snow event feedback can energize the evapotranspiration, hence reduce the runoff. In addition, the changes in precipitation characteristics with warming can alter the runoff in various ways. And we know that the accurate representation of these processes in models are very challenging, and we think this is kind of main cause of the uncertainty in runoff sensitivities. So here are our research objectives. First, we want to quantify the model bias in runoff sensitivity. Second, using this runoff sensitivity bias, we want to constrain future runoff projection. By constraining this, we want to identify whether the bias in this runoff sensitivity matter for the future projections or not. So we estimate the runoff sensitivity using multiple linear regression. Here, delta is 5-year average temporal variation for historical time period, both in models and observation. So here, runoff variation is function of precipitation and temperature variation, and alpha and beta is regression slope, which indicates the precipitation sensitivity. So alpha is precipitation sensitivity, which indicates the runoff changes per unit precipitation increase, and beta temperature sensitivity is runoff changes per unit temperature increase. So here are the multimodal median runoff sensitivity maps for the CMIP6 models. So when we look at the precipitation sensitivity, the values are positive all over the globe, and actually the values are consistent between CMIP models. However, when we look at the temperature sensitivity, over the northern mid-latitude, the values are negative, but over the tropics and the southern hemisphere, even the sign of the sensitivity is not consistent. Then is this runoff sensitivity meaningful to represent the future? Does this runoff sensitivity capture the effects of climate change on runoff generation? To answer this question, we use the runoff sensitivity from historical simulation to predict each model's runoff projection. Here we multiply each model's historical sensitivity with each model's projection of precipitation and temperature. So left is the original model simulation, and right is the prediction using this model historical sensitivity. As you can see, these predictions have very similar pattern to original simulation. And for each basin, we do additional statistical tests. We check whether these two have indistinguishable multimodal median and significant intermodal correlation. And as a result, we found that the historical runoff sensitivity can skillfully predict the future changes in 97 among 131 river basins. So basically, this runoff sensitivity is meaningful and it can represent the future uncertainty in the runoff changes. Then how biased is the model sensitivity? To check this, we need the observational data set and we use the observational proxy. So this is machine learning based global runoff reanalysis data set, which use the random forest model to generate the global runoff. This data set have 100 ensemble members, which enables the quantification of observational uncertainty. And zero data is shown to be outperforming the reanalysis data. However, the data is still not reliable for some basin, and we need to be cautious. So above is observed runoff sensitivity, and below is model sensitivity. When we get the model bias, for precipitation sensitivity, model tends to have more positive values. And for temperature sensitivity, model tends to have less negative values. So how much these biases affect the future projection? To answer this question, we did observational constraint. Left is the prediction using runoff sensitivity. Here, we substitute the model sensitivity by the observational sensitivity. So our observationally constrained projection is observed sensitivity multiplied with the model projection in precipitation and temperature. This is resulting correction effect. This is observationally constrained projection minus original model simulation, and this is multimodal median map. As you can see, most basins have negative values. So overall, the observationally constrained projections indicate a drier future than the unconstrained one. And this correction effect mainly arises from the temperature sensitivity bias. In other words, the runoff decline due to warming is too strong in observation compared to the model, which leads to this downward correction. And when we get the results, when we do same analysis for the CIMIP5 models, CIMIP5 models have similar pattern to the CIMIP6 models. This indicates that the constraining effect is consistent regardless of model generation. And is this correction effect statistically significant? For each basin, we do below tests to answer this question. So first, our prediction by runoff sensitivity have to be similar to the model simulation. And then our observationally constrained projection have to be statistically different from the original model simulation. Next, our correction effect by observed sensitivity have to be larger than the possible correction effect from the non-stationary and internal variability of the runoff sensitivity. When all of these criteria is satisfied both in the CIMIP5 and CIMIP6 model, we consider the constraint for that basin is robust. So such robust basins are marked with a thick outline in this map. As you can see here, the temperature sensitivity bias is large enough to affect the future projection significantly over these Amazonia river basins, North Africa, Eastern Europe, Southeast Asia, and Australia. Then what is the cause of this sensitivity bias? At least to get the hint, for each basin, we get intermodal correlation between mean state variables and runoff sensitivity. So this is result for the precipitation sensitivity. Here we get intermodal correlation for 131 river basins and make a box and whisker plot. Here x-axis is each mean state variable and dashed line is statistical significant correlation. So as you can see, only the runoff ratio have significant correlation. And this indicates that fixing the mean state bias in runoff ratio may improve the precipitation sensitivity bias. However, when we do same analysis for the temperature sensitivity, no single mean state variable have universal correlation as in precipitation sensitivity. So we think that it is all likely to lessen the more critical temperature sensitivity bias if we only focus on mean state bias. So today's key point is like this. The runoff decline due to temperature increase is generally underestimated in ESMs. And this bias can be quantified by the temperature sensitivity using historical time series. Discussion. First, the degree of sensitivity bias is, of course, affected by observational data set. But when we do sanity check with the more reliable station data for available basins, the overall results are consistent. Second, to help reducing the temperature sensitivity bias, we have implemented runoff sensitivity metrics to the diagnostic package. So we hope the model developer can utilize this diagnostic to reduce the temperature sensitivity bias. So thank you for listening, and just let me know if you have any questions.
Do you want to put questions in the chat? Yeah. What do you think? There are some?
No, we should move on.
Oh, move on.
Yeah, if that's
Okay,
okay.
yes, that's fine.
Okay, so thank you.
Okay.
We're moving on for the benefit of time. And so next speaker is Danny Lund. Deriving historical dust emission variability with sedimentary floor records using an inverse analysis approach. And I think they're it's getting ready for me there. So you need to be
Okay. All right. Hello everyone. I'm Danny. I'm a postdoc at NCAR. We switch gears a little bit and talk about aerosol simulation in CTSM. So the talk, it's concerning a central question about how Earth system models simulate historical aerosol variability, and how is it actually changed in the past 100 to 200 years, and whether the models are able to represent that aerosol variability. And so this is basically the plot that we are showing using a bunch of CMIP6 models and the dust reconstruction. So the dust reconstruction is the black line that's compiled by using 19 paleocore records of decadal dust deposition for the dust reconstruction. So you see about 50% of increase in historical dust since the 1850s. You don't see that for CMIP6 models. They are mostly indicating flat trends of atmospheric dust. And here we're asking the questions why, because if they could not replicate the 50% dust increase, then there will be bias aerosol forcings in climate assessment. So we try to fix that biases in forcings. And it's just not just dust, but a lot of aerosol schemes, not just dust, maybe fire and bioaerosols, natural aerosols are biased to our present days and cannot be extrapolated to other climates. So that's something that we want to fix. And so the thing is that okay, so given that we have biased aerosol radiative forcings, we have different solutions. The long-term solution will be to fundamentally couple or improve mechanistic aerosol schemes better with climate change and land use change. But the near-term solution is now we want to fix it in those near-term climate assessments. So we need some quicker solutions. So the AeroCom people, will try to force ESMs to follow the observed aerosol variability. So that's the approaches that we are trying to take here. It's first to use paleo core records to globally tune Earth system model dust decadally and other aerosols decadally. And the second is to use paleo core records to derive global dust emissions data sets to drive ESM simulations. So this talk is going to talk about the second approach. We try to derive globally gridded dust emissions from the 1850s to the present day. Okay. So how do we do that? The approach is called the inverse analysis or inverse method, which probably a lot of you have some understanding of. So it basically involves some observations. So in this case, we have 19 core records of decadal dust deposition time series from the 1850s to the 2000s. We call that beta. So we have 19 time series. And then we have the state variables, which is the 7 dust emission time series from the defined regional dust source regions that we care about. So that's called lambda. And then the Jacobian or the sensitivity or the slope matrix that captures the dust deposition to dust emission sensitivity. So that's the partial derivative over there. And that's simulated by an ensemble of multiple climate models in the AeroCom. So the idea is pretty simple. So this is basically the main idea. We try to do an inversion using observations of dust depositions with the sensitivity to derive the regional dust emissions historically. So we use the cost function and we try to minimize the cost function decade by decade. So the idea is basically to try to force a set of 7 lambdas time series to match those 19 observed time series of dust depositions. And after that, we have those regional time series. We try to downscale it to a spatially gridded dust emission data set by using the simulated present-day dust emission pattern from those model ensembles. So just try to scale it decade by decade and region by region. And then we combine them together to form a historical dust emission data set. So that's the gridded dust emission data set from 1850 to 2000, and that's a decadal data set we called DustCom version 1. So this is the data set that we yield, and I try to visualize a little bit so that you understand what's going on here. So the color shows, so there are 7 colors here showing the deposition, the fraction of deposition supplied by 7 dust emission sources. So you see, for example, over North Africa, so there are several core sites that located over those regions where those dust deposition are 100% supplied by dust emissions coming out of North Africa. And there's, sites like the Ove sites that's capturing dust depositions that's supplied by mostly from dust from the southwestern United States, and so on and so forth. So you see core records over different parts of the world that sort of indicative of the historical dust emission variability over the 7 rectangular regions, that is the 7 dust emission regions that we concern. We try to infer emissions over those 7 regions. Except Southern Africa, you don't see any sites there. So we're trying to get more core records from over those regions. And hopefully we can do a better constraint over Southern Africa in the future. And then this is to show you the core records. So these are basically the 19 time series of dust deposition that we retrieve from the sedimentary core records, the ice core records, and peat and coral core records, and so on. So just to give you a rough idea that you are seeing a historical increase of, to different extent, but you see an overall increasing trend in the historical dust emissions since the 1850s. So the basic idea is to substitute these time series and then to do the inversion and solve for the 7 lambda time series. So that's the idea. I'm showing you the inversion results here. So these are basically the inversion results of the 7 lambda regional dust emission time series. So you see dust emissions over North Africa, dust emission over Middle East, and so on. And each of them have different increasing rates, but mostly you see an overall increasing rates. If you sum them up to a global total, so that's the global dust emission historically here, we successfully re-derived dust emission that increased by about 50% in the historical period. The Air Commit people asked us to provide future scenarios, which we have very little knowledge about. So we just try to re-derive some, assume some future scenarios. There's an enhancement and reduction and so on. And then in the past 20 years, from the 2000 to the 2020, we have very little interdecadal variability for dust, as shown by the satire data set. So for now, we assume no changes in our emission data set. And then we have 500 ensemble members for characterizing uncertainties. Yeah, so that's the future scenarios. And I'm just showing you the spatial patterns here. So this is a spatial pattern of historical dust emissions from DustCom version 1. It's simulated by an ensemble of global climate models in the AeroCom. And so, and then you also see the differences from the contemporary climate and minus the start of the historical period. And that, again, shows you about 50% increase across the century. The data set has a resolution of CSM1, so it's about 2 by 2.5 degree. And so what's interesting here is that we are trying to put this data set into CTSM5 and try to drive a historical 1851 to year 2000 land atmosphere coupled simulation. And so this is basically prescribed emissions. So CTSM5 is not simulating dust actively, mechanistically, but it's just taking prescription of dust emission from DustCom. Chem6 dust AOD is being actively simulated. So we have active simulation in Chem6. And then again, you see a very linear response in the dust aerosol optical depth of about 50% increase throughout the historical region. So it's a very linear response of dust AOD to the dust emissions. So that's interesting. And I'm showing you the time series here. So DustCom version 1, it's a decadal data set. So it changes every decade, but Chem6 is being actively simulated in this case. So we successfully replicated historical changes in dust. So that's the red line. So only the CSM2 DustCom run successfully replicated the dust reconstruction. The blue line is the mechanistic dust emission scheme, and we could not see that such kind of changes, and we need to know why. And but yeah, now we have a less biased aerosol simulation in the history, so hopefully we can fix that climate forcing very soon. So this is just evaluation showing the dust deposition is matching the core records pretty well. And then we did this AeroCom phase 3 dust radiative forcing experiment. So we have a bunch of global models using the DustCom version 1 data sets, dust emissions, to simulate a historical cooling in the dust. So just following the historical variability of the prescribed dust. And this is pretty big. This is not pretty big, but it's pretty significant. It's about 20 to 30% of the total direct radiative forcing of aerosols historically. So the value, the total aerosol historical forcing is about negative 0.5 watt per meter squared. So this is about 30%, 40% of it. Right. So the final thing that we are thinking about here, it's something that we can work on in the future direction, is to how to improve the ESM mechanistic dust in terms of the long-term variability. So we are wondering why the blue line is not working very well. It does not show a flat increasing trend historically, but if you look at the land use data set and things like that, there should be some increase in the crop cover and a reduction in the natural vegetation. So some of the suspects that we don't couple too well with land use, are the land use change, desertification, deforestation, water use management, and warming, and etc. So the dust schemes may have problems or issues coupling with these historical land use data set, as well as LAI variability could be really important in governing the regions of dust emissions as well. So there's an issue. It's not responding to the.
It's not going to the next slide. I don't know why.
Okay, good. Yeah, so this is a summary here. I just want to say that we have a new dust emission data sets that should be used to constrain our future development in the mechanistic dust scheme. And the dust cooling, it's pretty significant. It's about 30 to 40% of the historical direct radiative forcing of aerosols in the historical period. And some of our group members are also trying to develop similar approaches, using similar approaches to derive a historical fire emission data set, for example, using charcoal records. And so this is something, the mechanistic dust development, it's something that we will look into in the next step. So yeah, that's it. Thank you.
Anything online? Yeah. Okay, any questions? And maybe one question, right? And then we'll move on. Sean.
So you give some examples of, human impacts that would change that, but wasn't your emissions map mainly like large desert regions? So how do you?
Yeah. So it's mostly desert regions. So the rectangular regions are the historical, the desert regions, and the models, most of the climate models are only able to simulate natural dust from the desert areas. But you need to know that, right, the observations, the dust depositions, they don't know whether, the observed dust, they don't know where it is natural or anthropogenic or agricultural. So there must be influence there. So we're just attributing all of the variability in those core records to the natural emissions, to the desert emissions. And that's right.
Thank you.
Thank you.
Is next.
All right, so yeah, this is trying to address the question of, is water availability from the land surface in arid and semi-arid regions being misrepresented? And so I want to acknowledge all the collaborators on this project, but also emphasize that we haven't really all had a chance to discuss this, so they're not responsible for anything that I say that's stupid. This is following on from a paper that we published last year, which argued that historical trends in near-surface humidity are being misrepresented in models. So on the left, you see trends in annual mean vapor pressure for ERA 5 from 1980 to 2020. And on the right, you see trends in the ISD station data. ERA 5 in these long-term trends looks very similar to the station data. So we're kind of trusting ERA 5. And if you look at the gray regions here, this is where the trends in ERA 5 near surface water vapor lie within the spread of trends from the CMIP6 models. So there are a bunch of regions that are not gray, where the trends in ERA 5 are lying totally outside of the distribution of trends you get in the CMIP6 models. You can also account for the local precipitation trends, and I won't go into the method here, but just show you this result. When you do that, you've got many more regions that kind of jump out as being distinct between the observation-based data and the models. And they're kind of almost all in the sense that they're relatively negative. So the trends in near surface vapor pressure in the observation-based data is relatively negative compared to what you get in the models. And when you kind of look at the characteristics of the regions that are exhibiting this discrepancy, it's mostly in the arid and semi-arid regions of the world, in particular, the orange regions here on the map. You can see correspond very well to where you see that discrepancy. And so if you just focus in on the arid and semi-arid regions of the world, this is showing the joint probability distribution of specific humidity versus precipitation trends. So this is the distribution across space. And that's for the CMIP6 models. That's what you get if you average over precipitation bins. This is the trend in specific humidity normalized by temperature. So it's in percent per Kelvin. And we can kind of compare that with what we'd expect from Clausius-Clapeyron scaling, where you see the model is just showing kind of an overall rise in humidity that's very close to Clausius-Clapeyron scaling. If a location has had a positive precipitation trend, you're slightly above that. And if it's had a negative precipitation trend, you're slightly below that. When you look in the observation-based data, the whole distribution is shifted down. So basically what's happening is models are showing this rise in humidity that's very close to Clausius-Clapeyron scaling, and observations are showing no rise at all over these arid and semi-arid regions. So previous studies had recognized that there were discrepancies between models and observations in near surface humidity trends. And I think our contribution in this study has been to kind of emphasize that this discrepancy is very closely tied to climatological aridity. And if you focus in on the arid and semi-arid regions of the world, the discrepancy is really big. And basically you have models showing rises in humidity that are close to Clausius-Clapeyron scaling, so apparently without any kind of limitations on water availability. And then the observations showing no rise at all. And so something is wrong, and that could have potentially severe implications. And so we want to understand what's going on. So now we're trying to understand the origins of this discrepancy and try and address the question, why is humidity rising in the models and why is it not rising in reality in arid and semi-arid regions? So here I'm just going to focus on the arid and semi-arid regions of the world, and I'm just going to be focusing on CSM2 for now. We'll expand to other models later. And I also just want to caution that this analysis is still much more preliminary than I would like it to be. In particular, I've only looked at ERA 5, and we had a discussion this morning that ERA 5 maybe can't be trusted on the high frequency variability. So definitely need to expand this to look more at the station data. But it's good, I think, to take advantage of all the expertise in the room and kind of hear what you think about these metrics. So we have a big long list of what potentially could be going wrong. And here I'm just going to touch on one of them, and that's this potential that models could have more water available at the land surface than reality. So basically what happens in the models, if you look out to 2100, this is averaged over arid and semi-arid regions, evapotranspiration just keeps on rising. And that's despite there being declines in soil moisture. And so what if in reality there's more limitations on how much evapotranspiration can be increasing? That could explain why we don't see this increase in near surface humidity that we see in the models. So what I've been trying to look at is search for any evidence for there being a discrepancy using daily variability. So I'm going to focus on daily average fields and deseasonalize. And then I'm going to consider the warm and the cold seasons separately, and also remove the seasonal mean for each year. So we're removing low frequency variability and removing long-term trends and focusing in on the kind of sub-seasonal variability. So here's the kind of traditional picture of soil moisture and evapotranspiration regimes that I think everyone here is probably familiar with. So we've got our energy limited regimes where it doesn't matter too much how much soil moisture you have. But then you have your kind of transitional regimes where it matters a lot for evaporative fraction how much soil moisture you actually have. So what if the model and reality in these arid and semi-arid regions are sitting in a different part of this kind of curve of regimes? Or what if the slope for how evaporative fraction varies as a function of soil moisture is different in the model compared to reality? And so I do want to look at FluxNet sites. I just haven't got there yet, and there were talks about that this morning. So that's definitely one of the next steps. But if you look in the models, soil moisture is pretty highly correlated with prior precipitation. So what you see here is just an example over Phoenix, where you're seeing soil moisture on a given day as it relates to prior precipitation averaged over the prior 10 days. And you can see they're highly correlated at that location. The map is kind of generalizing that to all the arid and semi-arid regions of the world. Similarly, near surface humidity is pretty highly correlated with evaporative fraction. So if you have a day that's characterized by high evaporative fraction in the model, you have higher near surface humidity, and that's kind of true throughout the arid and semi-arid regions of the world. So kind of given the limitations on observations of these quantities, I wondered if we could just kind of instead look at how near surface humidity is varying as a function of how dry it has been. And so that's what I'm going to do, but I am using ERA 5, so I guess you've got to take everything I'm saying here with a grain of salt. So let's think about what we would expect. So if we have a curve like this for observations of how near surface humidity is varying as a function of how dry it has been, I think if the model was less water limited, you might imagine that you would need it to have been drier before near surface humidity starts to fall off. And since we're in anomaly space here where they're all adding up to 0, I think the anomalies kind of in the energy limited part would be a bit smaller. Alternatively, if the kind of slope of this curve was different, I think maybe we would expect that just near surface humidity would be varying less with how dry it has been. So here's the curve that you get in the models for how near surface humidity varies as a function of how dry it's been. So this is taking all the arid and semi-arid regions and then averaging them. The top panel is showing the probability distribution of that prior 10-day precipitation. And so you can see that when it has been dry in the models in these regions, near surface humidity is very low. Here's what it looks like in ERA 5. And so these look very similar. Of course, we have questions now about whether we can trust the daily variability in ERA 5, but it does look very similar to CESM. And this is what you get. It's still using ERA 5 near surface humidity, but instead using GPCP precipitation. And that changes the structure of the curve a little bit, but not, I think, in the sense that it makes it look like reality is more water limited. So we do seem to have kind of a very similar way in which near surface humidity falls off as a function of how dry it's been. So this is averaged over all of the arid and semi-arid regions here. I'm just giving you a bit of an impression of what that looks like across space. So taking all of the arid and semi-arid grid points and binning them according to their climatological aridity. So we go from the most arid regions to the most humid arid regions. So you can see in the colors how humidity is varying as a function of how dry it's been. And that's the difference between them. And so there are some small differences, but overall, I think ERA 5 and the model here they're looking very similar. So that's for the warm season. Here I'm just showing you the same thing for the cold season. And again, they look very similar to one another. So the model seems good, I guess, if you can trust ERA 5, which I realize is a bigger question than I thought it was this morning. And so at least from this analysis with ERA 5, I don't think there's indications that there's more limitations on water availability in reality than in the model. Another way you could imagine maybe you could get at this is just by looking at the daily distribution of humidity. So for example, if the real world was kind of sitting like this, you might expect there would be a big kind of dry tail of humidity as it kind of falls off this cliff here. And if the model was more in the energy limited regime, maybe you'd have a narrower distribution. You could also imagine that if they're both in this transitional regime, but the slope of this was shallower, you would just have a narrower distribution of daily humidity in the model. When we look at the distributions of humidity, we don't see any evidence of that. So if anything, there's slightly larger distribution of near surface humidity in the model than in ERA 5. Again, with the question of can you really trust ERA 5? So then I was a bit worried with all these metrics. Are we just kind of looking at weather, bringing in moisture, and rain kind of together and not really telling us about what the land is doing. So I think maybe this is kind of more traditional metrics to look at like how do things vary after it's rained, so dry down events. So if you have a precipitation event, you maybe expect that humidity would rise, and then it would fall off on some time scale as the soil dries out and there's no more water left to evaporate. And if the model were less water limited, maybe you'd expect kind of less of a rise in humidity with the rain and then a slower gradual fall off after it's rained. So the methodology we're going to use here just was one season here over Phoenix to illustrate it. Just going to pick out rain events that are above the 99th percentile. And then make sure you don't have another rain event above the 95th percentile over the next 30 days. And then look at how does humidity vary after rain events in the following 30 days. So remember, this is maybe what we would expect if we were seeing different limitations in the water availability between the model and the observations. Here's what CSM2 looks like. So this is, on the left is the precipitation itself, and on the right is how near surface humidity averaged over these arid and semi-arid regions decays following rain events. And then that's what it looks like there in ERA 5. So again, I think this looks pretty similar to what we have in CSM2. This is again ERA 5, but instead using GPCP precipitation to define the events. And so overall, it seems like humidity falls off after rain events in kind of a similar way between the model and ERA 5. So if we can trust ERA 5, which is an open question, it looks like the model is pretty comparable. This is again just showing that as a function of space. So this is for ERA 5. The top is the precipitation composites, looking at how as a function of time, and how does humidity fall off as a function of time following precipitation events. That's what it looks like in CSM2, and then that's the difference between them. And so there are some differences in how humidity evolves after it's rained, but we're looking for something that can explain this kind of common issue across all of these arid and semi-arid regions, and they really don't seem to be that different, ERA 5 and the CSM2 large ensemble. So to summarize, a warmer atmosphere holds more moisture, and so with warming, you'd get an increase in water vapor, unless there's a limited availability of water, either from transport into a region or from evaporation. Earth system models show a rise in humidity that's close to Clausius-Clapeyron scaling, so they don't seem to have limitations on the water availability. And so here, and observations don't do that. So here, using daily variability, we've searched for some evidence of whether arid and semi-arid regions in reality are more water limited. Again, using ERA 5, so we need to check that we can trust that. But we find that the variations in near surface humidity as a function of how dry it's been are very well represented in the model compared to ERA 5. There's no evidence of a big difference in the distribution of daily humidity, and the evolution of near surface humidity after dry down events is also very similar between the model and the observations. So all these point toward the model being in a similar regime to reality, although my reality here is ERA 5. So we've got to check whether that's really true. So the next steps are to verify these conclusions with flux tower sites and other soil moisture and ET products, and definitely need to now look at the ISD stations for humidity as well and check that these conclusions hold. Search for time evolution over the historical record, and then continuing to investigate all of these other possibilities that I listed on the slides. So thanks.
Okay, so questions for Ayla? Anything on that? Oh, there is one, but you can go.
Okay. So Meg said, really nice talk. I looked at some fascinating work, and I wonder if it's possible to build on this with metrics like Mezzanine has created in Lean or SNAP.
Yes, definitely. I guess yeah, I'd like to know how much we can trust all of these other products that have underlying assumptions that may be similar to the models, but definitely, we have been looking a bit at the ESA soil moisture scatterometer product too. Yeah, I think we just need to look at all of the data and see if we get a common answer.
It looks like Paul's gonna make shirts for everybody.
Shirts.
Thanks, Paul. We appreciate it.
Well, I guess I'm just, I mean, I'm curious. It'd be interesting to see what, but I wouldn't be surprised if you find that the stations give you the same results as Aerofiles. But we'll have to see. Paul knows more than we do. But so if it's not like the model simulating present day wrong, what's the next hypothesis? I mean, you're trying to say here, but maybe the trend is wrong. So we haven't captured the difference in the state between the 70s to the present day in like soil moisture content or something like that. Could that still be a candidate?
Yeah, I have. Well, yeah, so Karen McKinnon and I have been looking at that ESA product and trying to look at, from looking at that, it doesn't look like the declines in soil moisture are wrong. So I think, yeah, so far I feel like everything has been ruled out. I feel like the one thing that remains though is the plants. And because the plant physiological responses we just wouldn't see in the high frequency variability, right? And I think that's the one that's going to be hard to get at with any kind of variability diagnostics. Yeah, my feeling is that so far everything's pointing towards there not being a problem with the water limitations and there not being a difference in how soil moisture is declining. So then we're left with these other possibilities. I do think there could be differences in how evaporation is responding to temperature. And I didn't present that because I'm not confident about it, but there does seem to be a bit of a difference in the daily variability. And then of course, the main trend is a rise in temperature. So I don't know if that, yeah.
That's consistent with Hanjun's presentation from earlier.
Yes.
That's where the bias is in runoff.
Yeah.
But you do feel confident that it's attributable to ET trends being bad?
I'm not confident about anything, but I think when in the model world, the moisture budget is showing, I think the humidity rise in the models is primarily coming from ET. But that doesn't rule out that the real world atmosphere might be having a transport that is opposing that is different. So this is the moisture budget where you can see that in the brown there, that's the model's convergence of moisture over arid and semi-arid regions. And it's the model's not converging more moisture. It's evaporating more. But it could be that the real world is diverging more moisture. But I would, if I had to place a bet, I would say that it's ET that's different. But it's very hard to diagnose this in the reanalysis because there's a big jump in the time series of moisture flux convergence. And there's also the possibility that the observations have some artifact. That's another one that we need to try and rule out.
So we have time for discussion. Oh, yeah, Paul, I think we're opening it up. We can continue with this conversation and then broaden the conversation to all the talks we've listened to. Paul, you can.
Okay, can you hear me this time?
We can.
Okay, good. This is something that might be related, and we actually, some of us talked about this last year. In the real world, the way plants work is that they won't have the same evaporative fraction or transpiration rate at all times of year, all else being equal, because there's a growing season, usually in the spring or, after the rainy season ends. And then there's at the end of a dry season or in autumn, then the plants dial back and they kind of go into this maintenance mode where the stomata shut down a bit and the transpiration rates will be quite a bit lower, even though the humidity is the same, the temperature is the same, the soil moisture is the same, the radiation is the same. And at least Will said that that's not in CESM. It's or in CLM. It's definitely not in the ERA 5 model. I don't know if that's in anybody's model in their ecology systems, where it's just always a function of LAI and nothing else. So I don't know if seasonality and shifts in seasonality could also be aliasing into what you're seeing.
Yeah. We looked a little bit at seasonality in the paper, and you could definitely see, so the discrepancies there are the whole year round in the arid and semi-arid regions. But it's also there in the humid regions, but only during the arid months of the year. And so there's the seasonality we've seen is tied to the aridity.
Okay.
I have been trying to look like across space as to whether there's a link between LAI and where the discrepancy is happening. And I think there could be, but I'm just not confident about it because there's not enough degrees of freedom. But yeah, that's a good idea to look, to think more about that. And yeah. I would be, if you have any suggested references, I'd be, happy to hear about that.
So in the chat, Lily mentioned that she's used some remote sensing products and saw similar patterns in arid regions. If you don't want your reality to be ERA 5.
Yeah. Okay, that's good. No.
And then Rosie added a comment that if the real world had stronger CO2 links to model closure than the models, then past stomata might have been more open. It might have had more ET than the real world. Might have PPE. It's all over the place. PPE can help with that. Where we adjust the model slope, help the model that does this.
Yeah.
Rosie's trying to talk.
I just wrote that down so that I could get it straight in my head.
The very first talk after the break is about adjusting stomatal slope.
Mm.
But
yeah, I mean the thing is we don't know what the ET was in the past, right? So we only know this humidity gradient for the since 1980. We don't know what ET was then. So it's possible that in the real world ET was higher. Right? If the real world has a stronger stomatal response to CO2 than the model does. Does that follow?
Yeah, I think so. I mean, I just put this up because it's showing how the different parts of ET respond. And I guess not knowing anything about this, I didn't realize how big the transpiration part is of the future trends. And you could imagine
it's big, but it could be bigger, right? It's just,
yeah. And particularly if you look out to like out to 2020, it's not, that decline hasn't really begun. And so
in this instance of the model, remembering that the stomatal slopes are all arbitrarily 8 in CLM5 for all the PFPs. And so it would be quite interesting. Yeah, Abby will answer my question later, probably.
We should explore this further, but we've looked at this. Dan, you've looked at this, right, Daniel? And we didn't see evidence, I think, in the PP that we could get something that was right. We should revisit that. But.
I mean, it's also possible that we don't have a model structure that would allow us to do this. We also have this, like, the hydraulic redistribution thing, which is going to pull all the soil moisture up from the deep soil and evaporate it from the surface if the plants don't evaporate it, right? So this is very interesting. I look forward to the next iteration.
Are we out of time? There is a break.
Because we can move the conversation.
Yeah, we can move the conversation to the lobby. Sean, do you want to ask a
We
question?
go for online. I had a comment about.
Oh, it's okay.
Yeah. It was just that, we have this dry surface layer parameterization in the model, but it's not tied to soil color. And that might be interesting to see how that might change the evolution of the soil color and therefore the albedo. Sounds like it would go in the direction that she was suggesting observations are in. I just want to make that comment.
Okay, with that, I guess we can end the session for break and be back at 3.
Yeah.
Okay. Okay, we're right at 3, which is perfect. So we're going to start the afternoon session, everybody, with Amy Liu, who's a remote speaker.
Hello,
Hi, Amy. If you want to share your screen,
yeah, can you guys
we can hear you.
see that? And then, can you guys see my slides?
Yes, we can.
Okay, great. Cool. I'll get started then. Hi, everyone. I'm Amy and currently a 4th-year graduate student at the University of Washington working with Abby Swan. And today I'm going to talk about our work on how atmospheric feedbacks can change the sensitivity of photosynthesis to small functioning within CSM2. And this work was done with a number of collaborators listed there. So to start, we know that small functioning at the leaf level can alter carbon-water fluxes with the atmosphere, and that can affect surface properties, which then affect climate at the larger scale. So, for example, plants can increase evaporative resistance of at the surface, and then that will affect temperature. So within CLM, we can modulate small functioning using this parameter called the Medellin slope parameter, or GUNM. And this is a parameter within the Medellin model for small conductance, which is this equation shown here. And intuitively, we can think of GUNM as something that represents water cost per carbon uptake, where a high GUNM corresponds to high water cost, and a low GUNM corresponds to lower water cost. So this parameter can be estimated from experimental and observational data, and that has been done before by Linnell 2015. And so this is a plot from their work on the climate space of showing the global climate space of temperature against moisture index. And where there is gray is where there's vegetation, and darker the gray is where there's more vegetation there. And where there's color is where we have data to estimate GUNM. And each color here represents a different plant group. And across this broad climate space, we only have a really small subset of places we actually have data. And if we expand the data we have at these points across the temperature space, which is this plot shown on the right here, we have estimated GUNM on the y-axis. We can see that this parameter varies across different plant groups, across different colors, as well as within each plant group, so within the same color. So for example, with this black arrow here, we can see the range across the plant group. I think that corresponds to deciduous angiosperms. And we can see there's a large range across this one plant group. And this corresponds within CLM to broadleaf deciduous. And we can see here that that particular PFT is in different locations around the globe. Another example are these orange points, which correspond to the broadleaf evergreen trees within CLM. And that's just a spatial map of where that PFT is distributed across the globe. And these two examples show that for each plant group, there is a large distribution of values, but we're assigning a single value for these PFTs or for these plants that are in different locations around the world. And with our work, we want to test the implications of that. So we'll be perturbing values within the ranges of these arrows. I also wanted to show previous work done by Liverell 2021 that has tried making a global spatial map of GUNM estimates using a model data infusion method. So that is this plot on the left here. And if we compare it, a similar plot on the right, which is the spatial map of default GUNM values used within CLM, we can see that the spatial gradient of GUNM is different between the two spatial maps. The color bars are supposed to be similar. So we can see that the colors don't really match. And so with our GUNM perturbation simulations, we also want to gain some insight on the spatial gradient of GUNM. As I alluded to earlier, we perturbed GUNM within CLM according to the 5th and 95th percentile from the Linnell 2015 database for each PFT. So this is a plot of different PFTs within CLM and their perturbation. So the solid square is the default value used within CLM for that PFT, and then the open shapes are the low and high perturbation. And I want to note here that the default value used in CLM is not the midpoint between the two extremes, and that the range of perturbation is different for each PFT. So for example, with this orange arrow here, we can see that the broadleaf evergreen within the temperate and tropical will have a really large range of GNM. So more specifically, the question we want to pose first is, how does model photosynthesis change with different GNM assumptions? And I'm going to toss two plots at you at once. So these two are spatial maps of the photosynthetic response to GNM perturbation. So on the left is the response to a low GNM perturbation when we compare against the default, and on the right is when we have a high GNM compared to the default. And what we can and here brown corresponds to a decrease in photosynthesis, while green corresponds to an increase in photosynthesis. And we can see here that photosynthesis generally decreases when we have a higher GNM, and it's largely brown in this plot, and it regionally varies with a low GNM. There's like a mixture of brown and green, depending on what region you look at. And these two simulations have atmospheric and LA feedbacks, and we were wondering if we would get the same results or the same photosynthesis response if we remove these feedbacks. And we're going to start with looking at the high GNM, because I think the answer is a little more straightforward there. So on the left here we have the simulation or the photosynthesis response to high GNM in the absence of atmospheric feedbacks and LA feedbacks. On the right is the plot we saw earlier with the atmospheric feedbacks and LA feedbacks. And we can see that both plots are quite brown and they look quite similar. It's just the magnitude that's different. So as the title says here, atmospheric and LA feedbacks amplify the photosynthesis decrease for high GNM. But then I want to pose the question if this decrease in photosynthesis is plausible, because these are rather large decreases in photosynthesis that we see on a scale of 1,000 grams of carbon per meter squared per year. And if we take a look at the change in LAI for the simulation with atmospheric and LA feedbacks, we can see that there's really large LA decreases in the tropics. And I think the combination of like the large decreases in photosynthesis and large LAI on a scale of 3 decrease in the tropics make the high GNM value in that region a lot less plausible. And if we look back to our plot of how much we perturbed each PFT, we see that the high perturbation for, as mentioned earlier, for the broadleaf evergreen tropical PFT is quite high, like this point over here is very high for that PFT, which is what the tropics are mainly consist of based off this spatial PFT plot. So this really just drives the point home that the high extreme for GNM is probably not that plausible. So now moving on to the low GNM perturbations. On the left again, we have the simulation where we have no atmospheric feedbacks. On the right, we have the simulation where we have atmospheric feedbacks. And just off the bat, looking at these two maps, you can see that the spatial map coloring is quite different between the two. And I think this shows that atmospheric feedbacks can change the sign of photosynthetic response. And to really pull out the regions where that happened, we made this map showing where there is showing where there's sign change between with and without atmospheric feedback. And so here, where there's color, there is a sign change in photosynthetic response, and the color is what kind of sign change between the two simulations. And today I'm going to focus on the Amazon to see why this sign change occurs. So in the Amazon, photosynthesis increases in the absence of atmospheric feedbacks, and photosynthesis decreases when there are atmospheric feedbacks. And we have two hypotheses as to why this may be the case. The first one is that the increase in temperature pushes planets beyond the thermal optimum for photosynthesis. But there's a caveat here that CLM does include a representation for acclimation to the higher temperatures, which would reduce the negative impact of hotter temperatures. Our second hypothesis is that an increase in VPD or an increase in atmospheric water stress would close stomata or decrease stomata conductance, which would decrease carbon uptake and decrease photosynthesis. And to test the two hypotheses, we used a set of perturbed meteorology simulations. So using these simulations, we attribute each of one of the two effects on photosynthesis, or how much we can attribute to temperature, how much can we attribute to VPD. And these simulations comprise of a control run and a run where temperature was increased while specific humidity was held constant. And the third run where VPD was increased via specific humidity and temperature was held constant. And so the temperature simulation does include changes in VPD. So it includes both the direct and indirect effects, and some degree affects VPD. But in the VPD increase simulation, where only the specific humidity was changed, that simulation will also will have solely the effect of VPD. So this is the plot or a bar plot showing how much we can attribute to temperature VPD. So there's 3 bars here. The green bar is the total response or photosynthetic response to low G1M. The pink plot is how much of that response can be attributed to temperature. And again, this includes both the direct and indirect effects of temperature. And the blue bar is how much of the photosynthetic response can be attributed to VPD. And we can see here that the green and blue bar have similar magnitudes. So here we say that the photosynthetic decreases under a dynamic atmosphere in the Amazon can probably be primarily attributed as a response to VPD. So I think there are 3 main takeaways or implications from our results. The first is that the high G1M extreme is unlikely in the tropics, since we saw large decreases in photosynthesis and LAI that are a little unrealistic. The second point is that the spatial gradient of G1M matters. If in the real world there were spatial gradient in G1M for each PFT, then CSM2 would over or underestimate local photosynthesis by up to around 40%. And the third point, which is that the atmospheric feedbacks may reverse photosynthetic response to low G1M. We saw that in the Amazon that plants were sensitive to VPD when we turned on atmospheric feedbacks. And I think this also is kind of related to the point Will brought up in his intro presentation today, that about different calibration for land atmosphere simulations. So if G1M were calibrated in a land-only simulation, then that calibration may give us poor answers within the land atmosphere simulations. Cool. And thank you for listening. Feel free to ask any questions or reach out if you have any follow-up questions.
Anything in the room?
There's a question from Paul.
Do you want to read Paul?
Sure. How can you separate atmospheric effects from the impact of climate biases in the coupled model?
Did you hear the question?
Yeah. I think I have the chat open. That's a good question.
I can chime in that our fixed atmosphere is the atmosphere saved from the coupled model, so they have the same atmosphere. There could still be bugs.
Yeah. It's the same as the default G1M simulation. Yeah, the atmosphere, we're seeing the fixed atmosphere. But
Trying to understand the second comment here, the second implication about this is, can you say more? I didn't seem like your results were talking too much about the actual gradients in G1M other than just different values of G1M. Is there something about the actual spatial gradient that's important? And
Yeah. So so let me pull up this slide here. So I don't think our simulations can tell you what the spatial gradient of G1M can be, but I think that it can tell us like if a certain G1M value could be or isn't plausible for a region. So I guess the point was more for that currently there's one G1M value to represent each PFT that may have plants and locations across the globe, but that but in the case for in this case like broadleaf evergreen tropical, we can see that G1M value may not be plausible since photosynthesis decreases around quite a bit in this region. And this is at 1 time CO2, pre-industrial CO2, and we know that plants don't actually lose half their leaves or decrease GDP by 50% or like by that significant amount. So it's kind of alluding to like if that's kind of alluding to like if there were a spatial gradient, or sorry, this is okay, so I think it gave us an insight on the spatial gradient of G1M. But yes, like sorry, that wasn't actually the right answer to I think that wasn't really answering your question. But it's saying that let me find the slide here, that if G1M had a value that was lower or higher than what is currently represented within the model. So for example, if G1M weren't one value for each single PFT and actually like varied based on where it were, then there would be a under overestimation depending on what region you look at. So for example, in the low, if we had a low G1M within I guess the Amazon here, then or just the Amazon, then it would be the model would currently be overestimating photosynthesis. Does that make sense? Or
Yeah.
I realize that like
All right, I think we'll move to the next speaker.
Yeah.
It might be a little bit of a
Terminology.
just that it's a little difficult to conceptualize, I think, what Amy's trying to explain.
I'm happy to talk more about it offline. Yeah, for sure.
Our next speaker is, thank you, Amy. Our next speaker is Montastir Maruf. Or Maruf.
Can you see the screen?
Put it in presentation mode, then we're ready to go.
Hi, can you see my screen?
Yes, we can.
Okay. Hello, everyone. My name is Muntasir Maruf, and today I will be presenting on robust impacts of land use and land cover change on regional precipitation. This research is conducted under the supervision of Dr. Sanjeev Kumar, and I will be discussing how LULC modifications affect regional and global precipitation patterns. So we know that LULC is a major driver of global environmental change. It influences climate, ecosystem, and society. It changes surface albedo and energy flux, which affects temperature and moisture balance. Eventually, it alters the regional climate. From literature, we have found that the impact of LULC on precipitation is uncertain, and it needs further investigation to improve climate predictions. It is important
Farouk,
to
can I
determine.
interrupt you just one second?
Sure.
We can't, the slides are not advancing correctly. Could you, what's,
Can you see my
so your
second slide
screen is
now?
not, oh, you're zooming in. We see your screen, but could you put it in presentation mode and then see if it'll work?
Sure.
Yeah.
Can you see now?
It's not in presentation mode yet.
Now I put it in a
No,
presentation.
maybe you need to share your entire screen because I
Oh,
wonder
okay.
you didn't share the
Yeah,
full
maybe.
screen.
Let me share it again. Can you now see it?
It has not yet. We don't see your screen yet.
I'm hitting the button of the share of the entire screen, but
So you have to
somehow
then
it's
select. So after, so you select the. I don't know how to.
there are
Select the
three options.
windows.
Yeah,
When you
window.
and click on that on the left. So entire screen, and then click on that. No, don't cancel. Oh. Okay, so now we see your screen, but you need to put it in
But
presentation mode. And when.
Yeah, now I hit the presentation button, but do you
Nothing's
see it in
happening on our
presentation
side.
mode?
All right, so go back to that. So unshare the screen and go back and share again, and click.
Okay.
So do that again. Otherwise, we'll have to. We could run the presentation from here if you want. Do you prefer that?
Yeah, I can do that, but yeah, from my side, if I hit the entire screen sharing, it doesn't let me do that.
Okay, so. Yeah, we'll share our screen. We'll share the presentation from here.
Okay.
And just tell me when you need me to advance.
Oh, yeah, could you please go to the second slide? Yes. Sorry about that interruption. So we know that LULC is a major driver of global environmental change. It influences climate, ecosystem, and society. It changes surface albedo and energy flux, which affects temperature and moisture balance. Eventually, it alters the regional climate. From literature, we have found that the impact of LULC on precipitation is uncertain, and it needs further investigation to improve climate predictions. It is important to determine whether LULC impacts are part of natural climate variations or caused by human activities. Figure 1, here we can see the figure 1. It is from Boysen et al. And we can see that there are no significant changes in precipitation patterns across mid-latitude due to deforestation in all the models. Could you please go to the next slide? Here are our objectives of the study. So we want to understand LULC impacts on regional climate, which will improve predictions and decision making. So we have used large ensemble climate data and limited sensitivity experiments to assess LULC effects. And finally, we want to evaluate how LULC impacts will evolve in a changing climate to anticipate future risks and trends. So in this study, there is one animation. If you click. So in this study, we used the year 1995 as historical period and year 2065 as future scenario. So we are interested to know that these green lines, which are no LU runs, are significantly different from CSM2 LE results. If so, then why and how? Next slide, please. So we have used 100 ensemble members of CSM2 LE output, and which are fully coupled, which means it is land, atmosphere, and ocean interactive. We used the output from 1850 to 2100 with SSP 3.70 future scenario. So this is our control output. And then we developed 4 members of CSM2 no LU runs. So basically, these runs have the same setup as CSM2 LE, but we used the land use scenario at pre-industrial conditions throughout 1850 to 2100. And we also developed 1 CSM2 runs to reproduce the CSM2 LE at Anchor machine. This is for validation purpose. And here we used regular land use change scenario. Here, figure 3 shows the percentage changes of crop cover in historical and future scenarios. Next slide, please. So here is our data analysis procedure. First, we have calculated the climatology from CSM2 LE 100 ensemble members from 1951 to 1980. And we call it grand mean. Then we subtract grand mean from CSM2 LE and CSM2 no LU. After that, we computed JJ seasonal mean anomaly time series. We have applied 30-year running mean to JJ seasonal anomalies to make the data smooth. And after applying 30-year running mean, we got this time series figure, which is the top figure. This time series is area average mean, where more than 15% crop cover change happens. And now the statistical significance. If we look at the bottom figure, we can see there are stippling, and stippling shows the statistical significance. So to get that, first we select 4 random CSM2 LE member and compute their mean. Then we compute the mean of 4 members of CSM2 no LU. We computed the difference between the 2 means, and we repeat this process 100 times to form a distribution. So the difference of LU and no LU is significant if it falls outside the 95% range of CSM2 LE distribution. And this is the distribution we just formed. Next slide, please. This is our model validation. We reproduce 1 CSM2 LU run in Anchor machine, as we mentioned, and validate with CSM2 large ensemble output. Here we are presenting precipitation and ET global average time series. Our CSM2 run, no LU run, our CSM2 LU run follows the same trajectory and very consistent with the CSM2 LE 100 ensemble members. And the blue lines, which is our LU runs, falls between the 100 ensemble members. Next slide, please. So this figure shows the historical precipitation difference between CSM2 LE and no LU. In easy words, This is LU minus no LU. And it is JJ historical precipitation. We can see that precipitation increases significantly in mid-latitudes due to the land use change. If we look at the North America and Eurasia, we can see that there is a significant change of precipitation. It increases significantly. And in South America, precipitation decreases significantly. So this change of precipitation is kind of close to the land use change map, as we have shown before. And here we can see it in the bottom corner. So the areas where significant land use change happens, these areas and around that areas show significant increase or decrease of precipitation. Next slide, please. And this figure is the same as the previous figure. Here we just add the ocean precipitation. We see that LU also influences global precipitation patterns, including the oceans. If we look at South America region, which is the bottom box, we can see that it is very evident land use change affects the oceans also. It propagates through the oceans. Next slide, please. And here is our historical and future precipitation difference scenario due to land use change. From the both picture, the left and the right, we can see that areas where significant land use change happen, precipitation also changes around that region. And for example, North America shows very high crop cover change, and it also shows significant precipitation increase both in historical and future climate. So it indicates that land use change has both local and global impacts. And the other region also follow the same pattern. Next slide, please. So this figure shows the time series of historical and future precipitation for both CSM2 LE and no LU. Time series also show that LULC influenced precipitation significantly in North America, Eurasia, and South America. If we look at the North America time series, we can see that there is no change of precipitation in no LU runs from 1890 to 2170. Actually, the trajectory is very flat. Whereas the LU runs, which are the gray lines, it shows the increasing trend after 1920. And same pattern happens in Eurasia. Next slide, please. So this figure shows the time series of historical and future ET for both CSM2 and no LU. Here we can see that ET increases significantly in the regions where precipitation shows significant increase, like North America, and the opposite pattern happening in South America. Next slide, please. So we tried to understand the reasons of LU-induced precipitation changes. LULC modifications influence precipitation patterns differently across latitude, which is increasing the precipitation in mid-latitudes and decreasing in the tropical areas. LULC changes affect precipitation by altering ET, which increases in mid-latitudes but decreases in the tropics. Irrigation amplified increased ET in the areas like Central Valley. There's one animation, if you could click. Yeah, like the Central Valley, California, Ogallala Aquifer, and Mississippi River Basin. So ET changes contribute to the precipitation variability both locally and globally by affecting atmospheric moisture transport and circulation patterns. LULC-induced cooling may also have a role. So we are currently investigating that. The increase in ET exceeds the increase in precipitation in mid-latitudes, which leads to overall soil moisture depletion. Next slide, please. So here is the summary of our findings. To our knowledge, this is the first time we have identified the statistically significant impacts of LULC change on global and regional precipitation patterns. LULC change increases precipitation in mid-latitude regions, particularly in North America and Eurasia, while decreases in South America. Changes in LULC-induced ET, coupled with atmospheric circulation, can impact precipitation locally and globally in CSM2. Next slide, please. So that's all from me. Here are some reference we have used in this presentation. Thank you for your patience. If you have any questions.
We go on to the next one, so we're going to the delay. Yeah, probably. Next speaker is, thank you, Marlon. Next speaker is Martin Bellan, also remote. I guess we stop sharing. I'll stop sharing. Martin, are you able to share your screen?
I will try. Does that work?
Yeah. And go, yeah.
You see the full screen?
Yes, we do.
Okay.
Go ahead.
Perfect.
Thank you.
So the title of the talk here is about STEM heat storage, and how we're using ground LiDAR to model the effect of the storage, of the heat storage. But I'm actually going to talk a bit more about modifying a radiative transfer model to account for that and other things. So this work is done in collaboration with Gordon Bonan, Hideki Kobayashi, and Denis Baldoki. So a bit of context. So the stems, they store heat, and that heat affects the forest microclimate. The absorbed radiation during the day is basically being released slowly at night, and it increases the air temperature at night and decreases it compared to if there was no wood to absorb radiation during the day. The studies that have been looking at the heat storage in the biomass, typically they use the simplified modeling approach, and there's very few experimental observations on this. These measurements are very hard to make. And basically, very often we just have some data on the stem or the trunk or the lower part of the trunks of the heat at different depths. So here we're using ground LiDAR to try to improve on that, on the way we're modeling the heat storage. So ground LiDAR, here I have this little animation at the bottom of, that's Harvard Forest. The thing I want to mention here is that ground LiDAR, one of the strengths is that it's able to distinguish what's wood and leaves in the data. And this is based partly on different reflectance between the two at the wavelength used by the laser. But this is very useful for looking at radiative transfer in forests. So the questions that I ask here, the first one is, how much radiation is being absorbed by the wood in a forest compared to leaves? The second one is, what's the role of the heat storage in the energy balance closure at the eddy covariant sites? Because it's known that eddy covariant sites, most of them, they don't have very good closure of the energy balance. And the stems are known to be a potential area where we can improve on the closure. But this is very difficult to measure. So here we're going to try to model it and get a sense of how important this term is. And in the end here, we're going to use a modified version of the Norman radiative transfer model, which is a one-dimensional model. We modified it to consider wood absorption and also the effect of leaf clumping. So I'm going to present this, and then the question is, how close are we getting to 3D radiative transfer model? So when we're looking at radiative transfer in forests, there's like, the first thing that comes to mind is leaf optical properties. So, and this is very different if we're in the PAR or the near infrared, obviously. The PAR is about 90% absorption, and the near is about 10% absorption. And so in the near, what we need to understand is that leaf transmittance is also usually very high. So a lot of these photons that are transmitted through the leaves eventually hit wood, which is only about 50% reflectance. So there seems to be a lot of absorption by the stems in the near infrared. And this is what we're looked at here in this. We used a few sites here. I'm showing Harvard Forest on the left side, and then Morgan Monroe on the right. And what we found is in the near infrared, 43% of the total energy that's being absorbed inside a canopy that is absorbed by wood. So this is significant in the near infrared. In the PAR, it's only about 10%, which is expected. But the near, we didn't really have a good estimate on this. So from here, we're trying to model the heat storage, how much heat these stems are storing during the day, and how is it released at night. And we need a few things. We need the amount of radiation that's being absorbed, so we have that now. We need some sense of like the size of these stems and how that changes with height, because a large trunk is going to be able to store a lot more heat, obviously, than a small branch. And that the LiDAR gives us this information. We need the thermal properties of the stems. This is something we can do. We have access to, and then we need the some kind of modeling approach to calculate the heat storage. So what we did here is use these three sites, which they have a different canopy structures vertically. We have ground LiDAR data for each of them. And then we use the 3D radiative transfer model that uses ray tracing to calculate the absorbed energy by the leaves and the wood in 3D space. And from there, we use the multi-layer canopy model, which is a modified version of the CanVeg model. And it's modified to consider the heat interception by the stems. So what it's looking like is something like this. This is looking at a single stem that's about 1.5 meters above ground. And the different colors refer to the temperature at different depth in the stem and throughout the day. This is an average for a month. And so what we're looking at, we're seeing that the surface temperature changes. There's a lot more variability in terms of temperature than at the center of the stem. And also there is a shift in the maximum temperature reach. So this is just telling us that the heat takes takes a longer time to reach the center of the stem. Here it's a stem that's about 18 centimeter in radius. So the green line here is the temperature close to the center of the stem. So it's taking more time for that heat to diffuse into the stem and then diffuse out at night. And on the right side here is the same graph, but for a smaller branch that's about 14 meters above ground and a much smaller diameter. So when we're looking at the CanVeg model outputs at these two sites, we've got, again, Harvard Forest and then Morgan Monroe on the right. And then we're looking at the slope of the relationship between the sum of the heat fluxes and the available energy, so the net radiation. So the green line is the relationship without considering the STEM heat storage. And the red line is the relationship when we are considering the STEM heat storage. And this is what is telling us is that we've got about 23% increase in that slope. So this is just confirming that it's a significant amount of heat that's being stored in these stems according to the model. And it is helping to close the energy budget at these sites. So the results I've presented so far, they're looking at they're derived using a 3D ray tracing model, which has obviously a lot of complexities and it's difficult to compute all this. So now what we would like to do is use that knowledge and modify a simple one-dimensional radiative transfer model that accounts for the main aspects of these 3D effects and includes the wood also. So two things I need to mention here is leaf clumping and recollision probability. So what I'm showing on the right side here is this is a branch from the top of a canopy. It's a very different scale than what the other presentations we've been looking at, but this is so the top 25-meter canopy, and this is a maple branch. So you're seeing that these leaves, they're gathered together. You know, there's this very dense foliage around the branches, and this is clumping, what we call clumping in radiative transfer terms. It means that this has a few implications. So what happens when you've got leaves that are clumped like this around branches, it allows more light first to penetrate deeper in the canopy and reach lower layers. And the other thing that happens is that if a photon hits a leaf and doesn't get absorbed, it has a pretty high chance of hitting another leaf inside that branch clump. And this is what we call in radiative transfer, we call it recollision probability. And it's typically decreasing a lot your albedo because it's increasing the chances that you're going to have a lot of interactions between photons and leaves. So what we did here, we're modifying the Norman one-dimensional radiative transfer model. And this is the main slide the main message that I would like to pass in this talk is in this slide here. On the left, I've got the Norman model, which the way it's typically used, is very similar to the two-stream model, the same principles behind. If we're not considering any wood interception, no recollision probability, no clumping, we've got very high albedo. Typically, that's what's going to happen. And when you get this in the model, you might be tempted to adjust the leaf optical properties to correct your albedo because you know albedo is easy to observe. We can measure that from the ground or from satellite. So you know your albedo is too high, so you might be tempted to adjust your leaf optical properties, but that would have some other effect on the leaf energy balance inside the canopy. So what we're doing here, as we go towards the right, we're including on the second column here, we're including clumping, the leaf clumping. And what happens is we got a lot more light penetrating towards the deeper layers and reaching the soil. So we've got a lot of absorption by the soil. And in the third one, we're including the wood interception. So we got a lot of wood intercepting light, absorbing light. And on the fourth one, we got the wood interception and the recollision probability, which brings the albedo down and is very close now to what the 3D ray tracing modeling would give us, which is, I suggest probably close to reality. At least we know that the albedo is reasonable, and we know that the amount of absorption by the soil is also reasonable. So this is just in terms of the absorption or where the irradiation is going. And this was for the near infrared. By the way, this is the vertical profiles comparison between the modified Norman ray tracing model and the 3D ray tracing, or the Norman radiative transfer. And we see that the vertical profiles, they're in pretty good agreement for the wood on the right side, the sunlit leaf here on the top left, and the shaded leaf on the lower right. So we got a very good agreement now between this modified radiative transfer model and the 3D. So what we're learning from this, what I want to suggest here is that the ground LiDAR here is helping get better observation of canopy structure. Its the main goal is to guide the improvement of simpler models that can be applied at larger scale. These model outputs, they're highly sensitive to clumping profiles because it has a big effect on radiative transfer. These are difficult to observe. We don't have a lot of these observations, and we're still trying to gather some more data on how variable this is within plant functional types. So we're, in the end here, trying to improve the agreement between observations, like field observations or satellite, and the model parameter outputs in a way that reduces adjustments that we could be making to models and that would lead to effects that are difficult to trace in the end. So that's the end of the talk. Thank you for your attention.
Let's have one question as we transition to in-person speakers. Robert Allen is our next speaker. So yeah, if you would like to get up and take one question.
Hey, Renato, can you unmute yourself?
Yes. Hi. Thanks, Martin, for the very nice talk. I wonder if in your plots, like those are very detailed plots, and I'm sure you measure a bunch of things. But did you take like a snapshot of one part of the season? Because from your plots, probably wouldn't change much the optical properties like reflectance and transmittance of the wood itself, unless it's wet, right? Unless it's wet, and then it will be a little darker than if it's dry. But the leaves themselves, they would change with the seasons. So they would go very green in summer, and then they will grow kind of yellow in autumn. Did you look into the seasonal variability of the optical properties of your leaves?
No, not at all. No. I mean, this is one of the areas I feel like we have so little data on this. And it's not just leaf reflectance, like it's leaf transmittance as well. And leaf transmittance is actually really difficult to measure correctly in the field. And I feel we don't have nearly enough data to look at this variability correctly. I mean, just getting data, reliable data for transmittance for one site for one snapshot is already difficult, I feel. And this is one area where we could use a lot more measurements. That's what I would suggest.
Thank you.
Move on to our next.
All right, so I'm going to be talking about the chemistry, climate, biogeophysical response to tree restoration. Just some quick backgrounds. Trees obviously sequester CO2. This is known as a biogeochemical effect, and it's thought that this would help mitigate climate change. However, trees also have biogeophysical effects, including things like decreased albedo, increased evapotranspiration, and these can either enhance or diminish the negative impacts from biogeochemical effects. In addition to these two effects, there's also atmospheric chemistry effects through short-lived climate forcers, largely driven by BVOC emissions. So these impact things like methane, ozone, as well as secondary organic aerosol. There's a few studies that have tried to understand how trees impact SLCFs. And overall, more recent studies show that the impact of trees on SLCFs leads to a positive radiative forcing, largely due to the aerosol effect. So I used some CAM6 model simulations to try to further investigate the impacts of tree restoration on these short-lived climate forcers. This includes a tree restoration experiment relative to a control simulation with interactive atmospheric chemistry, and a comparable set of simulations without interactive atmospheric chemistry. And the difference between those two simulations allows you to quantify the atmospheric chemistry effects due to tree restoration. So these are slab ocean model experiments that I integrated for 200 years, and I'm looking at the last 150 years for the signal. In addition to these slab ocean model experiments, I performed similar experiments, but with fixed sea surface temperatures and climatological sea ice, which then allows you to quantify the effect of radiative forcings and the rapid adjustments. An important point here is that all of these simulations use prescribed atmospheric CO2 concentrations, so they do not include the biogeochemical effects of tree restoration. However, one can infer a biogeochemical estimate on surface temperature using the transient climate response to cumulative emissions, which I'll talk about at the end. So this is the land use perturbation, land cover perturbation that I used in these simulations. So change in crop is panel A, change in tree is panel D. And this is based on a multi-step procedure that involves both reforestation and afforestation. Reforestation is based on comparing the present day land cover to the pre-industrial value. And if there's an increase in tree in that grid box, I assume I use that tree cover area in the present day. That's reforestation. Afforestation is similar. It builds off of step one, but I look at end of century SSP projections. And if there is an increase in tree fraction in a given grid box relative to step one, then I use that tree fraction. So this results in a 12.3 million square kilometer increase in tree fraction, which is about 135% of the United States square area. And another important point is that these are time slice simulations. So this perturbation is instantly imposed. And the idea here is we're focused on a biophysical upper limit of tree restoration. So here's the surface temperature results. Interactive chemistry is on the left. No interactive chemistry is in the middle. And then the chemistry effects are in panel C. So overall, these biophysical effects are leading to warming, particularly without interactive chemistry. The net effect of chemistry, as you can see in panel C, is cooling. There's a hemispheric contrast where there is much more cooling in the southern hemisphere as compared to the northern hemisphere. So chemistry effects result in net cooling with a hemispheric contrast. So the next couple of slides try to understand why that is. The first step of that is to look at the surface energy balance decomposition. This analysis is done at grid boxes where the change in tree fraction is at least 0.1. So this offers kind of a regional or local interpretation of the mechanisms. So the albedo component is in the top panel A. So the albedo component is the main component that leads to warming under both chemistry and no chemistry. In terms of the turbulent heat fluxes, panel D and panel E are showing you latent and sensible heat. Latent heat leads to a large cooling effect in the southern hemisphere under both chemistry and no chemistry. And this is consistent with an increase in ET due to tropical trees. But the main takeaway here, in terms of the difference between chem and no chem, has to do with the downrolling shortwave term, which is in panel B. Okay, so there's more cooling when you have interactive atmospheric chemistry due to a larger cooling effect from downwelling shortwave radiation. We can then break up that into both a clear sky, which is panel G, and the cloud effect, which is panel H. So the big difference is the downwelling shortwave clear sky, which suggests the importance of enhanced scattering due to secondary organic aerosol. We can look at a broader view now. So again, interactive chemistry is on the left, no interactive chemistry is in the middle, and the chemistry effect is on the right. So the first row is showing you the change in secondary organic aerosol burden. As expected, there's a large increase due to the chemistry effect, largely in the southern hemisphere. This in turn is associated with a decrease in the aerosol direct radiative effect at the top of the atmosphere. That's the middle row. And again, this is largely in the southern hemisphere. And then the bottom row is showing you the change in the cloud radiative effect at the top of the atmosphere. So again, most of that is showing you a negative cloud radiative effect, largely over the southern hemisphere oceans. We can also look at the fixed sea surface temperature ones that I previously described to try to understand the mechanisms. So chem is on the left, no chem is on the right, and I've decomposed it into the northern hemisphere and southern hemisphere response. So the effective radiative forcing in the northern hemisphere under both chem and no chem is positive, which is consistent with a warming. Most of that warming is related to the instantaneous radiative forcing, the green bar, which is obtained from the surface albedo radiative kernel. You can see that under chem in the southern hemisphere, the effective radiative forcing is essentially 0, black bar in panel C. And that is due to a relatively large negative rapid adjustment, which is the blue bar in panel C. We can then decompose the rapid adjustment into its components, which is what I'm doing here. So things like surface temperature, tropospheric temperature, water vapor, and clouds. And the important takeaway here is that, again, down here in the bottom left, the relatively large negative rapid adjustment is due to a relatively large negative cloud rapid adjustment. So the two pink bars, these are two independent estimates of the cloud rapid adjustment. One is based on the kernel difference method, and the other one is based on the ISCIP simulator. And then finally, we can compare these biogeophysical effects to the biogeochemical cooling. This is showing you a time series of land carbon for both chem in blue and no chem in red, broken down by hemisphere and the global total. So as expected, there's an increase in land carbon storage. We can then use this transient climate response to cumulative emissions to estimate the corresponding biogeochemical cooling effect. And we find that chem gives a cooling effect of minus 0.35 K, and no chem gives something similar. So overall, the biogeochemical cooling effects are dominating relative to the biogeophysical warming. And so to summarize, I already gave you the first point up there. So the biogeochemical cooling is dominating over the biogeophysical warming. Biogeophysical warming is largely due to this, the albedo term, right, surface darkening. The important thing here, though, is that the biogeophysical effects mute 58% of the cooling, biogeochemical cooling under no chem. But when you include interactive atmospheric chemistry, that muting effect is much weaker. Okay, it's 20%. And when you include the methane effects, it's 31%. The reason for this, the reason for the larger net biogeophysical cooling when you include interactive chemistry has to do with both enhanced secondary organic aerosol as well as a relatively large cloud response. And then finally, there's a very strong hemispheric asymmetry due to tree restoration, and this in part is due to the chemistry effect, largely due to the cloud response over the southern hemisphere oceans. I'll stop here and take any questions.
Does the hemispheric asymmetry lead to large-scale changes in precipitation?
Yeah. There's a shift in the ITCZ, yeah, which is consistent with the relative warming of the northern hemisphere compared to the southern hemisphere.
So that change the, I don't know, does that damp the apparent increase in GBV that you would get from afforestation? Quantify that?
I'm not positive about that one. Yeah, that's a good question.
There's a question from Joshua. You want to go ahead?
Yeah, do you see any changes in nighttime behavior? I mean, everything you're talking about is sort of daytime stuff, but there's still haze at night.
I have not. Yeah, I haven't analyzed sub-monthly data for this, so I can't comment on nighttime versus daytime effects.
Thanks.
Shall we switch to the last talk of the day is Gordon Bonin. And then any remaining questions we have, I think, a few minutes for discussion at the end, right? Yeah.
Really fun day already. I hope I can end it on a good note. I know that stouts are waiting, at the end of this. I will just say that I don't like stouts, so I really don't care. I might talk long, but I'll try to go okay. But with that, I want to say that this is some work that Sean Burns, Ned Patton, and I have been doing to compare a multi-layer canopy model that we've been developing with observations for a walnut orchard in California. We're learning some things about that, about how to model plant canopies, and I want to sort of share those insights with you in this presentation. And so this is the slide that I always show when I introduce the multi-layer canopy. The left-hand side is the diagram of like the details, and the right-hand side is more about what I want to focus on this talk. And it's this idea, this phrase that the physics and physiology of the multi-layer canopy are simpler and more consistent with theory than is CLM's big leaf canopy, which has much ad hoc parameterizations and technical debt in it. And I always say that, and I never explain what I mean by that at all. So this talk is all about explaining what that is about. If you want to know some details, I guess the slides didn't translate correctly, but there's some papers out there, and we're working on one, and we do intend to actually publish this paper, but it's just taken a long time to get everything together. But maybe in April we'll submit it. Don't hold me to that, Sean, but yeah, we're going to try. The observational, that's an inside joke with Sean and Ned. The data set we're working with is a walnut orchard in California. In the canopy horizontal array turbulence study, it was instrumented with towers. The towers had sensors at multiple heights through the canopy. And what you can see on that lower right-hand panel is what I like about this is you can see some really complex temperature changes in temperature structure or profiles through the canopy over a very quick period. And this, in just 5 hours, you're seeing a very big change in the temperature structure through the canopy. So it's like it's a very rich data set to work with and to test a model. And so this is an example of the what you can do with the model and comparing it to observations. This is looking at wind speeds in the month of May. It is the period when the leaves are out. We have stratified the data into 5 different periods based on stability. But just to orient you, the vertical axis is height through the canopy, and the height and the canopy top is 10 meters. Horizontal axis is wind speed. And what you see is the profiles of wind within and above the canopy. The left-hand side is under unstable conditions, and the right is near neutral and stable conditions. And what you're seeing in all these different cases is there's a logarithmic profile of wind speed above the canopy. And then when you get in the canopy, it switches to an exponential profile. And that inflection point is really important for the turbulence that's generated by the canopy. The open circles are the model, the solid circles are the observations, and the model's doing a really good job at capturing this behavior, or this pattern, this profile. And the thing I want you to take home from this is a couple of reasons why this is really important. One is that the wind speeds in the upper canopy are very strong. And this upper canopy is where you have high net radiation. So you think the leaves would be really warm, but high wind speeds, it's easy to dissipate the heat through boundary layer conductance, and that affects the leaf temperature. lower in the canopy, smaller wind speeds, lower boundary layer conductance, it's harder to dissipate heat. So this vertical profile of wind is actually really important to getting fluxes and temperatures correctly. And the other point I want to make is that what we're looking at here is an analytical solution to the one-dimensional momentum conservation equation. So this is very much grounded in theory. And so let's look at what CLM is doing. It's a little different. In developing the biosphere atmosphere transfer scheme in 1984, Bob Dickinson made this assumption that the wind speed of the canopy is equal to friction velocity. And he notes that that is of adequate accuracy for the present model. Well, 41 years later, it's still of adequate accuracy because CLM is doing exactly the same thing. The code, there's a little snippet of code there for what's called UAF, wind speed on the foliage. It looks complicated, but it simplifies to friction velocity. And in CLM6, there's been a second wind speed has been introduced into it called an under canopy wind speed. And I'll get back to that later. But what I want to say here is that we have this wind speed in the canopy that's equal to friction velocity, but friction velocity is a measure of turbulence. It has the same units as wind speed, meter per second, but it's not a wind speed at all. There's this under canopy wind speed that's been introduced with biomass heat storage. And we also have like this 10-meter wind, and there's some wind that's used in fire spread. I don't know what that is, but there's some. So we have multiple winds in CLM that may or may not be consistent with one another. The other example I want to go through is sensible heat flux, because this is going to relate to that under canopy wind speed. Again, with a multi-layer canopy, you have a profile of sensible heat flux within and above the canopy. This is exactly like that diagram for wind speed. Unstable conditions on the left, near neutral and stable conditions on the right. If you're looking at these unstable conditions, what you see is there's very low sensible heat flux near the ground. The sensible heat flux increases in magnitude as you get higher in the canopy, and then above the canopy, it's constant with height. And the model is actually replicating those observations pretty nicely. On the on the stable side, you see something different. The lower canopy is a source of sensible heat during those did not come out at all, I don't think. What you're supposed to see is actually positive values there on the sensible heat flux in the understory, and negative meaning a source of sensible heat, and negative fluxes in the upper canopy, meaning a sink of sensible heat. And again, the model is capturing that pretty nicely. This is based on a first order turbulence closure scheme. So again, it's very soundly based, in terms of what it's doing. CLM does something different. It's a big leaf canopy. And so it has fluxes from, wow. I actually looked at this last night and everything was fine. Something went terribly wrong. So at least I tried to check this, but there should not be a flux of heat pointing down. That arrow is from the vegetation to the canopy air. There's also a flux of heat from the ground to the canopy air, and from the canopy air to the atmosphere. What I want to focus in on is this bulk sensible heat flux from the ground to the canopy air. It's parameterized in terms of the difference between the ground temperature and the canopy air temperature divided by a resistance. And there's nothing wrong with that. That's the classic formula that everybody uses. But what is this under canopy resistance? Because again, we can go back to Bob's paper in 1984, and he parameterized it again in terms of a temperature gradient, and then he had an exchange coefficient times this wind speed in the canopy, this UAF. Well, in CLM6, we're doing exactly the same thing. It's been done in terms of resistance notation, but you'll see that these equations are algebraically exactly the same as what Bob did in 1984. What we've done over the years is play around with the terms that, wow, nothing. I wonder what happened here. Oh, that we played around with this exchange coefficient, the CS term. It was a value of 0.004 in 1993 in Bob's BATS model. In CLM3, it changed to vary with the density of the canopy, decreasing to a bare soil value as the leaf area or plant area goes to 0. In CLM4, it was modified for under canopy stability. In CLM5, the under canopy stability was taken out. And then in CLM6, it's now been replaced with this under canopy wind speed. And what I mean by that is this is the actual, again, on the right, we're seeing actual code. There's that wind speed in the canopy, which is friction velocity. There's this under canopy wind speed, UUC. And what you're seeing now is if you're not using biomass heat storage, this exchange coefficient, this term here, is still using the wind speed, UAF friction velocity. But if you do the biomass heat storage, you're switching to this under canopy wind speed. So you're changing the aerodynamics under the canopy with the biomass heat storage in a way that has nothing to do with the storage of heat and biomass. And that's the cautionary tale I want to make sure you get from this, is that the conceptual framework of which this is being done has not changed in over 40 years. We've been playing around with this exchange coefficient, the CS term, and now the wind speeds, and those seem to be adapted as needed for a particular model configuration. But we're also now changing the under canopy wind speed and introducing that, but that's changing the turbulence. So that's not anything related to biomass heat storage or the storage of heat in the biomass. The other example I want to get into on this is roughness, length, and displacement height. Because the roughness length, just everybody to remember, is an empirical parameter used in the Monin-Novikov similarity theory. The multi-layer canopy replaces that with observable canopy-imposed parameters, in particular a leaf drag coefficient. And then the key point I want to say here is this displacement height emerges from the roughness sublayer theory, and it depends on the canopy flow. And this is just a time series over 4 days of the displacement height, the red being the model and the black being observations. And you can see displacement height varies depending upon time of day. And the model does a really good job of replicating that. And it varies by over 3 meters. And remember, this is a 10-meter tall canopy. And the displacement height is varying depending on time of day by 3 meters. Let's look at what CLM is doing in terms of roughness, length, and displacement height. And what it's doing is it's treating these as canopy structural parameters. They vary with the height of the canopy. They vary with plant area index, leaf and stem area, and that's all they depend on. In CLM5, we use this approach from Zhang and Wang. In CLM6, it's been updated, a new approach by Meyer et al. In 2002. And what they did is they took a parameterization from Mike Raupak from 1994 and fit that to the FluxNet data. And this on the bottom right is just showing you what these different things look like. This is for a broadleaf deciduous forest, the ratio of roughness length to canopy height as a function of plant area index. And you can see some differences between CLM6 and CLM5 in the red. There's a third option of Fates. When you're running with Fates passes the roughness, length, and displacement height to CLM. That depends on canopy height. Then CLM adjusts that for plant area index using Zhang and Wang as in CLM5. So this is like a hybrid mashing or whatever of everything. But the point I want to make here is I actually tried to figure this out, and thanks to Adriana and Eric for helping me try to figure this out. What I could figure out is to do all this stuff, it's 5 subroutines in 4 different modules, and there are 6 different variables and 2 different data types. And it was hard to figure out what's going on. If you really want to see it, I have a flow chart of what's going on at the end, but I'm not going to show that. But the point is that CLM and Fates are treating roughness, length, and displacement height as canopy structural parameters, not as turbulent flow parameters. And then that leads to scientific debt and how these are used throughout CLM. And a really important one is that the forcing height in CLM is actually taken to be the height of the atmosphere above Z naught and D. But remember, I've just told you that in the roughness sublayer theory, we calculate it, D emerges from the turbulent flow. So how can you calculate D if you don't know the forcing height to get the turbulent flow? But if you don't know the turbulent flow, you can't get D. And so everything, this is just an example of how there's these ideas sort of perpetuate throughout the code. And as you try to do something different, you have this sort of what Mariana Vertenstein used to call a peeling onion effect. And this gets really messy. and smelly and ugly. And this is an example. We don't know what the forcing height is in, in this case, if you don't know the rough displacement height. The last example I want to work through is just the canopy physics. And this is what we're really trying to solve is a complex system of equations. And what I mean by that is the fluxes depend on the canopy states, and the states depend on fluxes. And a really simple one is stomata conductance. That depends on leaf temperature, but the leaf temperature depends on stomata conductance. A more complicated one is the Oberkopf length, depends on latent and sensible heat fluxes, but the latent and sensible heat fluxes depend on the Oberkopf length. And this is a point that's been known for a long time. Mike Raupock and John Finnegan had this sort of nice paper, and of all things, a book on modeling stomata function and stomata physiology. They were talking about how the physiology of the plant community influences the microclimate, and the microclimate influences the physiological state, so neither is independent. So in this book about stomata physiology, they write a chapter about turbulence in plant canopies, because they were saying that's what you got to get right if you want to get stomata right. So what does CLM do? CLM uses this iterative solution to solve these fluxes. And by iterative, I just mean there's a series of calculations that you go through, you hope it converges, and then when it does, you stop the iterations. The standard configuration is 40 iterations, but there's also a fast configuration that does just 3 iterations. This, I don't expect anybody to read this. I did this just for shock, because this is actually text taken from the tech note. And first of all, I want to say kudos to Keith Olson, because this is text that Keith Olson put together where he actually deciphered and figured out what was going on in this iterative calculation of canopy fluxes. The main point I want to say here is it's a 37-step solution to get this right. And so I just wanted to see, could I even get this on a slide? And this is what it looks like if it's on a slide. I do want to focus on 3 things, 3 points of this iteration, because I think these are really important. One is if the model is changing sign, if it's flip-flopping between stable and unstable conditions, in this iteration, you just turn that off completely. You say the atmosphere, we don't know what the right one is, whether it's stable or unstable. We're just going to set it to neutral values. Well, that completely changes your answer right there. If the latent heat flux changes sign during this iteration, you set the latent heat flux to 10% of the computed value and add that energy to the sensible heat flux. Or if the leaf temperature changes by more than 1 Kelvin during an iteration, you take that excess energy, that energy imbalance, and add it to sensible heat flux. And I hate to say, we're a state-of-the-art model, and yeah, this is in the code. You can see this stuff in the code. And so with the multi-layer canopy, we invested a lot of time over the past year now, and that's been what's delaying the publication, finishing the paper in numerical methods. And what we've done is we have a 5-minute time step in this model instead of CLM's 30-minute time step. We're using 4th order Runge-Kutta to integrate the system of equations forward in time. And we're interpolating the forcing from 30-minute to 5-minute. And what you can see over here on the right is just this time series. It is a 6.5-hour period of a particular day. We're looking at the data points are every 5 minutes. It's the sensible heat flux. And if you look at the black line, which is just the 5-minute time step, you can see the sensible heat flux is bouncing all over the place. And this is bad. This is what we don't want. This is what those ad hoc fixers in CLM are trying to solve. If we go to the 4th order Runge-Kutta, which is the blue line, you can see you're really smoothing things out really nicely. There's always one time step where it's off. And that's related to storage of heat in the canopy air. And then if we interpolate the forcing to the 5 minutes, that sort of step change in forcing that's occurring every 30 minutes gets smoothed out. And then you can see in the red lines, we have a very smooth fluxes now. The point of all this is over here in the lower left. Advanced numerical methods can eliminate the need for ad hoc fixes. And so I want to just wrap this up with a thought about what we can do moving forward. And again, this is a great paper by Mike Raupock and John Finnegan, where they frame this dichotomy. multi-layer canopy models were deemed correct but useless. Correct meaning you can actually represent the physical processes correctly, but useless in that at that time there wasn't enough data to implement these models. They were computationally inefficient, and so you couldn't use them. The big leaf canopy was considered to be incorrect but useful. It is the wrong, it's wrong, it's not doing things right, but it's useful in that you can implement it in a model, a global model, and you can tune it up and you can get reasonable answers out of it. Well, what I want to say is I think there's a third alternative here. I think there is something called a correct and useful model. And wow, okay, none of this makes sense anymore. The arrow should be going right. Rotate those in your mind. Or actually, the CLM one should be to the right. But anyway, CLM is somewhere in this incorrect and useful space. The multi-layer canopy is somewhere, it's in the correct space, and it's borderline useful, meaning that you can actually do some interesting simulations with it, but under very limited sort of cases, very narrowly defined cases. So what does it take to actually get to a correct and useful model? Can we actually get there? Because if we do get there, there's a whole lot of interesting new science we can do. You can actually directly observe leaf fluxes of photosynthesis, stomatic conductance, leaf water potential, leaf temperature. You think of the implications for canopy chemistry in terms of BVOCs and dry deposition. What I'm particularly interested in is this notion of forest microclimates. The overstory is very different from the understory. And then something Marisa Legou introduced was this idea of the orphan canopy airspace. When the CLM couples to the atmosphere has a lowest level. That level is typically something like 30 or 40 meters. There's air underneath that, but nobody treats it. CAM doesn't treat it, CLM doesn't treat it. It's this airspace that nobody deals with. And that's what she meant by the orphan airspace. But it's also this air where we live. We live, organisms live, it's where life is occurring, is in that airspace. And that's what she's calling the ecological climate. And so don't we really actually want to be modeling the air where we live? And that, I think, is the true reason for doing a multi-layer canopy model, is to enable this science. But that's it for the air. I'm done. Too bad. I'm sorry the slides didn't work out. I'm not quite sure what happened there, but it's a mystery to me.
Sean. When you did the change to the time stepping, what does that do like in the standard version? Does it help any of those kind of things, or do they exist regardless of the step?
There are a couple ways of going with that, answering that. We can run the multi-layer canopy with a 30-minute time step, and that looks really, really terrible. The whole idea of a 5-minute time step was that it actually, at the 30-minute average, it smooths things out. But then what we've done recently was go and actually look at the 5-minute data itself. And that's where we're noticing all this sort of variability and fluctuation. The 30-minute average is smooth, but the 5 minutes that get you, the 6 5-minute values that get you that 30-minute average or what's bouncing around, that's what we didn't like. And the point of this is that this is not coupled into CLM. It runs what Adriana tomorrow will call an offline sort of unit testing is how we do this. But when you couple back to CLM, you would still be running at this 5-minute time step. It's just that you would then accumulate the fluxes over that interval and then pass them back to CLM and CAM that way. So the coupling with CLM and CAM is always 30 minutes. It's just that the time step is 5 minutes. Is that helping you with this?
No, I mean, I was wondering, like you showed some of the problems, like the flip-flopping, the need for 40 iterations. I was just wondering if any of that goes away if you were to. Okay. Kind of idea.
Okay. So that's the other way of going. So I can do this. I can play around with time step in the multi-layer canopy because it is very simple. It's this uncoupled from CLM code, and I can do whatever I want. When you get into CLM space, it becomes a lot harder. I would have no idea how to do this sort of sub-time stepping in CLM. That sub-time stepping is done for soil hydrology. So you can do sub-time stepping within CLM. But in terms of this massive 37-step process, I would have no idea how to do some time stepping within this.
How do you explore other numerical methods, like other numerical solutions differ in the same way? Or
No, yeah, so, like with the Summa model, when Martin was, Clark was putting together the Summa model, he did a different sort of way of doing numerical methods where you actually are doing more of just sort of this straightforward Eulerian time stepping. But what he's doing is he's, meaning you could use a 30-minute time step, but he's actually solving a system of equations simultaneously, and he's calculating all the partial derivatives. If we go back to this point here, what Martin is trying to do with Summa is calculate these dependencies through partial derivatives and stuff like that. And then you use like a Newton, I should say, actually using a Newton-Raphson approach or so to update the canopy fluxes and states. We haven't done that. Yeah, that might work. What I would say is like, I'm not quite sure how one gets all the partial derivatives that's needed to do that. Meaning, like, you really do need to know the change in stomata conductance, the partial derivative of stomata conductance with temperature, and I'm not quite sure how all that stuff gets done in a multi-layer canopy. So that concept might be much more difficult in a multi-layer canopy.
Any questions online or not? Any other thoughts about any of the talks?
This may be more of an observation. I think I've seen talk of CTSM 3.1 being a machine learning enabled version of the model. And so I like what he's going to do by adopting ML for multi-layer scaling.
That was one of my better decisions.
And actually, maybe it's not machine learning. It's actually, but we're talking about it.
Yeah, we can be sufficiently vague about that.
That's a backup. So maybe we should invest similar software engineering resources into the multi-layer canopy as we might machine learning capabilities.
So 0.
Zero.
Okay, we could do that.
We can do that. 0, yeah. All right.
Great.
So
Great.
end of day.
End of day.